Thank you everyone very much for coming to this course. Really exciting for me to be here as well in Barcelona, first time. I think a lot of PhD students, and maybe other kinds of researchers here as well. Hands up if you're a PhD student. Okay, almost everyone. Hands up if you're not a PhD student. Okay, are you a master's or undergraduate students or postdocs? What are you? Masters. Okay, masters. You're working? Okay, you're just interested. Okay, yeah, welcome. Okay, great. And I think we've got people online as well, right? How many people do we have online at the moment? Okay, and they can all hear and see me okay. It's all good. All right, great. So just want to say, if you feel you have trouble understanding me, just put your hand up and like ask me to repeat. It's no problem. Or ask me to talk slowly. No problem at all. Okay. So my name is Stefano Albrecht. I'm an associate professor at the University of Edinburgh in the School of Informatics. And I'm very happy to be here to teach you a little bit about multi-agent reinforcement learning, which is a really hot topic in AI and machine learning and something that we have worked on a lot. So I'm first going to spend just a few minutes to introduce the course, to give you some background information, and then we're going to switch gears and get into the slides for the course. Okay. So let me first introduce my group. We're the Autonomous Agents Research Group in the School of Informatics. Here you see a subset of the people. We're about 20 people, postdocs and PhD students. And we're very much hardcore focused on deep reinforcement learning, multi-agent reinforcement learning, and more broadly speaking, machine learning algorithms for autonomous systems control and decision-making. That's what we do, basically. That's our daily business. We are housed in the School of Informatics. I want to say School of Informatics is by a wide margin the largest computer science department in the entire country. It has about 160 full-time professors. It's very large, has a long history as well. A lot of research going on. It's also historically one of the oldest AI institutes in the world. So in 1963, there were only 3 AI labs in the world, at MIT, at Stanford, and at Edinburgh. A lot of the early work came from Edinburgh. And it's also ranked by the UK government as the #1 computer science department in the UK for research power and impact. So it's a very strong place. And if any of you ever visit Edinburgh, it's a beautiful city, but feel free to reach out, then we'll be happy to show you around and team me up with some people in my group and show you our department. There's a website here which has a lot of resources for PhD students and other researchers. I'll say more about that in a second. Okay, so broadly speaking, we want to create autonomous agents that can accomplish tasks in complex dynamic environments. And here I'm showing you a few example applications that we're actually actively working on. On the left, there's an example where we have a warehousing application. I'll show you some videos of this later. In the center, there is an example of self-driving. I was for a number of years involved with a company where we were building self-driving vehicles, and our company was bought by Bosch a couple of years ago. And now we think with Bosch, we're Europe's largest level 4 self-driving team. And then there's a few other example applications. So in all of these applications, what they have in common is that you have to develop these highly sophisticated autonomous systems that can process constant streams of data and make safe and informed decisions. And something else that's in common here, and that's kind of the focus of what we're doing today, is that there's not just a single actor, there are multiple actors that coexist and they have to interact in some useful, meaningful way to solve a task. So it's a multi-agent system. I mentioned the website earlier. The website has a lot of useful resources, and I want to just take a minute to tell you about that. First, we have a blog, which you can find here. There's a number of blog posts on there which summarize all kinds of useful information. Many of these blog posts are summaries or tutorial-style posts which introduce concepts in reinforcement learning and multi-agent systems. So, for example, in deep reinforcement learning, there's a lot of secret sauce, a lot of secret implementation sort of tricks that you have to use to make it work. Unfortunately, these things are never explained in the papers, but when you look at the code, it's full of stuff. And we decided to collect it all in a blog post. You can see it. Other blog posts about an online talk series that we organized at the Alan Turing Institute, multi-agent environments, basic mistakes that were done in sort of propagated in the research community in the early days of multi-agent reinforcement learning. So lots of really useful blog posts for you to check out. The other useful resource I want to share with you is our code repository on GitHub. We have many actively maintained code repositories with all kinds of algorithm implementations that you can use. But maybe the most important one, especially for today, is our IIIA-CSIC code base. This is a research prototype code base for multi-agent reinforcement learning. It has a standardized interface. It has, I think, 10 mature implementations of algorithms. It has all kinds of environments you can plug and play, and it has all kinds of configuration sort of knobs. So if you want to quickly get into multi-agent reinforcement learning and plug and play, this is a starting point for you. We published this at NeurIPS a couple of years ago, and it's been picked up by the community a lot. So lots of other papers are building on it, for example, or building on the algorithms. So it's a good starting point. Okay, but maybe the most important resource I want to share with you is this new book that we just finished writing and published with MIT Press. This is the first and only textbook ever that introduces this field of multi-agent reinforcement learning. It's published with MIT Press. It's available on the website here, available for free. In fact, you can get the book PDF. You can also get all the slides that I'm going to be using in this week. And also there's another code base that we released with the book, which is designed to be very easy to use. So in contrast to IIIA-MARL, the thing I said earlier, which is very sophisticated, this code base is very easy, like small, self-contained, easy to read. That was the point of that code base. So if you're really very new to this type of work, then this might be the best starting point for you. And the book is designed to be self-contained. It has chapters on reinforcement learning, game theory, deep learning, deep single-agent reinforcement learning, and then talks a lot about multi-agent reinforcement learning and engineering aspects. And you can already pre-order the book on all kinds of shops like Amazon, and it will come out in print just a few days before Christmas. So everyone, please go ahead and pre-order the book and help me live a more luxurious life. Okay. By the way, a question. So we're really happy with the design for the book cover. Does anyone have an idea what this might mean? This actually has a pretty cool meaning, the spiral you see there. Don't be shy. Any hands up if you have any ideas about what that might mean? Yeah? Okay, interesting, but no. But interesting idea, yes. Any other ideas? Anyone online who wants to guess? Okay, I'll tell you. So this is an abstract graphical depiction of a mathematical process where two agents are repeatedly interacting, and in the process, they are learning to converge to a fixed point, which is in the center. And in this case, it would be a Nash equilibrium. So imagine the two agents play a game of rock, paper, scissors. The two dots are the two agents. The two dots are the two agents. The links between the two dots means one interaction, okay, one time playing, and they keep repeating the interaction, and then they spiral into the center, and in the center there's this fixed point solution, which is a Nash equilibrium, which in rock, paper, scissors means that everyone plays all actions uniformly randomly. It's pretty cool, I think. It's beautifully sort of summarized abstract depiction. Anyway, this is the book, and if you have the time, I recommend that you check out the chapters before the days this week, so you can have an easier time following the lectures, or you can go back to the chapters after the lectures and just to revisit. Course overview, so we have a few days here. We'll be mostly be following the chapters in the book, for which you can get the slides on the book website. Some other things we're going to spend more time on, some other things we're going to be doing fairly quickly, and some things we're going to be skipping altogether. Okay, so this will be a sort of a dynamically paced course. Sometimes we spend more time, sometimes it'll be quite fast paced, but you can always go back to the book chapters and take your time. There will also be coding exercises. So one of my co-authors, just for this course, he put together three very small coding exercises that shouldn't take more than maybe 1, 2, or 3 hours that you can do yourself in the afternoon. And the link to that will be released on the Slack. I think everyone here should be on the Slack, and there's a channel for coding exercises. So this is optional. We're not going to be discussing this much. We won't be grading anything, but it comes with files that explain step by step how to run some of these algorithms, how to get some results, and so you can get started and get playing. So it's completely up to you whether you want to do this. All right, so just a warm up. I want to ask just Ron, so why do you want to learn about MARL, multi-agent reinforcement learning, and what do you want to do with it? Hands up. I really would like to know from you why you actually care about this. Don't be shy, right? It's just an interesting way to start a conversation. I think we have a microphone there. Yes.
So I'm working on football analytics and
Okay.
as an application for multiple agents on the soccer field. That's why, and there are some advances right now that use reinforcement learning and in imitation learning right now. But I think multi-agent is a more applicable scenario here.
How can you use multi-agent reinforcement learning for football analytics?
So simulating the game in general and getting more results. So we don't have a lot of counterfactual information right now from the data that we have.
Okay.
So creating that.
So you want to learn policies for your players to see what they would do in certain situations.
Yeah.
Okay, interesting. Yeah. Right. Anyone else? Why do you care about MARL? What do you want to do? Hands up.
Hi, so I'm working on automated negotiation, and I think it could be one way to train agents to learn how to negotiate with each other, or vice versa. I think negotiation could actually maybe help existing moral problems or solutions
Okay.
to improve. If the agents can negotiate with each other how to solve a problem, maybe in that way it could help.
Okay.
And I've recently seen a lot of papers talking about moral in combination with negotiation, but I never knew much about moral. I had to review those papers, so I realized I need to know more about this topic.
Okay. If I could just ask, what university are you from?
I'm from here. I'm working at this institute.
Ah, okay. And you? Where? Oh, what's it called? Okay. I'm actually from Germany, but I can't see, tell what you're saying. Ah, okay. Okay. All right. Who's up next? Who wants to say up here?
I'm a PhD student. I'm working on formation control for multi-agent robotic systems. I'm implementing it with like consensus-based algorithms, and I thought I just wanted to explore some more reinforcement learning applications, especially for allocating where the agents would be in a formation or just task allocation in general. I was always interested, so this was a perfect opportunity.
Yeah, nice. What university?
University of Manchester in the UK.
Oh, okay. Yeah, right. Yeah, I think we're beginning to do some collaborations with some guys in Manchester.
Yeah, exactly.
Okay. All right. Maybe one more. Who would like to say why are you interested in multi-agent reinforcement learning? What do you want to do with it? Okay, I'm going to use my volunteering algorithm. Okay, there's someone there.
Hi, I work like in the healthcare industry, and I saw a curious paper that talks about a counterfactual strategy for drug discovery.
Okay.
And also, maybe if like it would be nice or interesting to learn more about MARL. I just like the topic for treatment strategies for regimen.
Nice. And what university are you from?
I actually did a master's here in the UV, but I'm just working now.
Oh, okay. Yeah, nice. Right. Great. Thank you. Yeah, I think we might come back to this maybe in the other days as well, just cover other people. All right. Good. I think I'm going to switch to the actual slides for the book now, but before I do that, I just wanted to remind you, go check out our research group website, which has a lot of useful resources. And I want to say this now rather than at the end, just make sure I don't forget. After this, if you want to get even deeper into the field, there's a few more events coming up that I'm helping to organize. In the UK, there's the Alan Turing Institute, which is the National AI and Data Science Institute, named after Alan Turing. And we are organizing the second UK Multi-Agent Systems Symposium, which brings together all kinds of labs in the UK and Ireland that do multi-agent systems research. And you'd be welcome to come if you happen to be in London at the time. And we actually so there will be no attendance fee, so you can come if you're a student. And then the second thing is I'm program chair for a big reinforcement learning conference, which will be in Dublin next year in June. And so lots of big names in reinforcement learning and multi-agent reinforcement learning and robotics and so on will be there. But also there will be lots of people who care about cognitive science, psychology, and behavioral economics who also care about reinforcement learning. So it brings these communities together. And there's a website here, rldm.org. And there you can check out already. Good. I think with that, I'm going to switch to the actual book slides. Let's see. Okay, so introduction. As I said, you can get all the slides online from the book website. In fact, we're going to try and polish them even more, but the current versions you can get already on the book website. By the way, if you know any professors who care about reinforcement learning or multi-agent reinforcement learning and would like to teach, please tell them that there's this amazing book now and also the slides, and they can use the slides in the book for free to teach. So We want to spread it as much as possible. Okay, so I mentioned already the book. You can get it on the website. Introduction. So we're going to talk just a little bit about multi-agent systems. What are they? Why do we care? And then what is learning in multi-agent systems and some challenges involved as well. Okay, introduction. If there's any questions, feel free to just put your hands up. Okay, we can get your question. All right, so multi-agent reinforcement learning, or MARL, is about algorithms that try and find optimal decision policies for two or more artificial agents that interact and coexist in a shared environment. Okay, so the algorithms want to learn policies for multiple agents that coexist in a shared environment. We use reinforcement learning, it's in the name. So we want to interact and learn by observing what's happening if we take certain actions. And we want to improve over time. And the goal is to learn these optimal policies. There's lots of exciting applications you can try and tackle with multi-agent reinforcement learning. Here's just 4 examples. There is computer games. I'm going to show you a video in just a second. Autonomous driving, mentioned earlier, something I was heavily involved in where we can use this. Robot factory warehouses, we'll show you in a video in a second as well. Automated trading, for example, eBay, you can have automated agents, or on travel agency websites, you could have an automated agent that organizes your whole trip. Let me switch slides again because I've got a few videos. So who knows what this is? Can anyone see what kind of game this is? Yes, StarCraft 2. Yes. And this is just a sort of an example I wanted to show you for something that we did. So I'm going to show you what's happening here. There's 2 teams. This is a real computer game. StarCraft 2 is a super popular computer game. There's professional leagues with people who make money living playing this game, basically. And it's huge, a huge fan base. We control the red team, which has a number of different units. There's these Marines that can shoot. And then there's these bigger units that have bigger guns, basically. And then there's these flying units that can heal. And then there's the blue team, which we're trying to destroy. And that's controlled by a built-in AI, basically. And it looks like this. So we use multi-agent reinforcement learning and the red team has first spread out to increase fire patterns. And you can see that the healing unit is focusing on the high energy assets to keep them alive for as long as possible. You can see that our units have learned to concentrate fire on the center points, and then they take out the high energy assets of the opponent last. And basically, we learned to completely dominate the opponent very quickly. We did not tell our team anything about teamwork or strategies. We didn't tell it to spread out. We didn't tell it to focus fire patterns. We didn't tell it to heal in a particular way. We left it to the algorithm, and the algorithm learned on its own how to develop these sophisticated teamwork strategies. It's a pretty cool thing if you think about it, right? So there's this complicated game, and the algorithm figures out a good way to do teamwork. So that's like a very basic example of a small task and multi-agent reinforcement learning, but actually you can scale this up and do some pretty big things. So who knows about AlphaStar? Who has heard about AlphaStar? Hands up. Okay, some people. AlphaStar was one of these big show-off projects from DeepMind where they basically played the entire game of StarCraft 2, not just a sort of a isolated battle scene, but actually they played the whole thing from start to finish against professional players. So that means you start with just a building and some building units. You have to build your whole base. You have to collect resources. You have to build your whole army. You have to work in partial observability. When there's fog of war, you cannot see everything. You have to spread out, collect information. You have to then harass and attack your opponent and do some pretty sophisticated attack maneuvers and strategies. And basically, here's a video. You can find many videos on YouTube where they look at the replay, and then these moderators basically they look at what's happening, and then basically in this case, there's a guy on YouTube who is basically talking you through what's happening. I'm gonna mute him, just about my voice now. But basically, there's in this case, AlphaStar controls the one of those races, which is called Protoss. And then there's the built-in AI, which controls the Zerg, which are these alien guys. And basically, you start from zero, you build your building, you collect resources, and you play out this entire game. Basically, it's really quite impressive if you see what kinds of maneuvers the Protoss player, the built-in the multi-agent reinforcement learning approach discovers. Basically, the way it's trained is with a leak or population-based training, it's called. So you train a policy using deep learning for your own team, and then basically you repeatedly expose your own policy, your own team, against a pool of different kinds of opponents that you collect over time. Basically, that's what's called population-based training. And in that sense, you can grow and become better and better and better. You can identify weaknesses that you then exploit. You also identify your own weaknesses that you then have to close. And you want to also remain resilient against these previous attacks that you saw. So you have to keep them in the pool as a type of memory, basically. And you can train and train, become really strong. Okay, so these are computer games, but what can you do in real? Here's an example for a warehousing application that we are actively building in my lab with a very large warehouse automation company called Dematic. So Dematic operate everywhere. They're this gigantic warehouse automation company. They build these very high density robot systems for warehousing systems. And basically, we want to use multi-agent reinforcement learning to see if we can optimize the operations of these systems. And here is actually a few snapshots for a high fidelity simulator that we built with our engineers. And these are real warehouses in different places in Europe that we represent. So there's a small, medium-sized one, large warehouse, and a disjoint one. The disjoint one means that there's a sort of a cold compartment and a warm compartment, and they need to be kept separate because of the thermodynamics. And basically, what's happening is that there's a bunch of humans. We call them pickers because their task is to pick items from the shelves. They're the pickers. And then there's the AGVs, which is a bunch of robots that coexist in the warehouse with the humans. And the robot's task is to be at the right place at the right time to collect those items from the humans and bring them back to the packaging station. And we want to use multi-agent reinforcement learning to basically optimize the heck out of the system. So we train policies for both the robots and the humans. The policies are displayed to the humans on an iPad, basically. And for the robots, they go into the brain. And then they operate in this warehouse. So here's an example for a real warehouse in Germany for a car parts manufacturer. And basically, initially, you see that the agents are swarming out, and then the orders keep coming in, order, order, order. Imagine like an Amazon warehouse with lots of requests and orders for different items. And basically, the different agents, they work through the warehouse to basically work through all the different orders that keep coming in. And this looks like a beehive to you. It's like no discernible logic, but you can do a lot of analysis and understand that they're doing some really sophisticated ways to coordinate basically with individual robots servicing multiple humans at the same time. And as a result of this, we actually recently opened a real prototype test facility in Germany in a city called Dortmund, where we're actually building these real systems and we're transferring the trained policies into the real environment now. And the Dematic will actually commercialize this as a product as well. So this, I think we can say this will be the world's first real industry scale application of multi-agent reinforcement learning. So it's a really nice result. Okay, so this was just to show you a couple of videos for motivation. And I'm going to try and go back to the other slide. Okay, back here. So just to get you excited about some cool things you can do. All right, so what's a multi-agent system? I think we need to talk about this just to make sure we're all on the same page. Multi-agent system primarily is defined by two things. First, there's the environment. Environment is a physical environment, for example, a warehouse, or a software-defined environment like eBay, for example, or a computer game. And basically, there is a state that evolves over time, which is influenced by the actions of the agents that live in this environment. So that gets us to the second point. The second part of the environment is the multi-agent system is these agents. Okay, agents are virtual entities, pieces of software, basically, that receive information about the state of the environment. They can see certain things using different modalities, and then they can choose certain actions to influence the state of the environment. For example, they can walk around, they can pick up things, they can sort of shoot in StarCraft and that sort of thing. And importantly, these agents are goal-directed, so they want to maximize what's called their rewards or the returns. We're going to talk about it in the course of this week. But basically, they're goal-oriented, which means they have defined goals, and they're choosing actions to try and achieve those goals. Here's a sort of graphical depiction of multi-agent reinforcement learning. At the bottom, you have your environment. I'm just using a square to represent that. And then there's these circles. The circles represent the different agents. Each agent is defined by certain actions they can take. They make observations from the environment, basically take actions in the environment. Agents may have different kinds of domain knowledge. For example, they may have knowledge about the dynamics of the environment and other things. And of course, as I said, they have goals. Agents may also be able to communicate with one another by sending messages or symbols, basically. So it's sort of a graphical description of a multi-agent system. And of course, you can build this in any kind of way you see fit. So I already showed you some applications that you can imagine I've represented in this way. Here's a very basic example that you see a lot in the book. Basically, it's a toy environment that you can use for basic training and experimentation, and it's easy enough so you can actually understand what's going on. So we call this level-based foraging. This is a 2D spatial environment, a grid, basically, a grid world. And let's say in this example, there's 3 agents or these black robots. Okay, you see these black robots, these agents. And they have various skill levels, which are the numbers that you see there. So in this case, skill 1, 2, and 1 again. At the same time, there is these items shown as apples here, and they also have different skill levels. And basically, the agent's goal is to collect these apples in as quickly as possible. But the interesting aspect here is that they may need to collaborate in order to do this. So the agents can only pick up an apple if they're all situated around the apple, and then the sum of the agents' levels is at least as high as the apple's level. So if you see in this example here, the agent on the left here with the level 1 is not able to pick up that apple because the level is not enough. So you can imagine it means it doesn't have the skill, it doesn't have the capability or the capacity. On the other hand, the 2 guys on the right here, they collectively are skilled enough because 2 + 1 is 3, which is the level of the apple, so you can collect that apple. And so you can see what's happening. Sometimes they can do things on their own, and sometimes they may have to dynamically bond with one another on the fly in order to pick up certain apples. And then they can sort of disband again and do their own thing. So it's a very dynamic sort of team formation aspect here as well. And in this case, they have certain actions. The action space is to just go up, down, left, or right, try to collect, or no operation, no op. I think there was a hand up here. Yeah. Yes. I'll repeat the question was, in this example, are the agents fixed or can they enter and leave basically? In this example, and in fact, in the entire book, we just assume that there's a fixed number of agents. It doesn't change. So in this case, if there's 3 agents, there will always be 3 agents. But there's a lot of research that looks at what you're suggesting, which is open environments where agents can disappear and enter at any point in time. So in my group, we've done a bunch of research in this area as well, which is really interesting. And you know, there's lots of course, realistic applications where you have to worry about this, that the agents might disappear. For example, asset loss in defense applications or, you know, in your games, for example, and then reinforcements basically coming in, right? Or there was a mention of soccer earlier, soccer or football analysis. You know, players can disappear as well, which could affect the teamwork strategy. So it's a very important question. But here we keep things simple. All right, so this is a basic example, and we're going to be using this a few times in the lecture, and you see this a lot in the book as well. And in fact, you can use this yourself if you use any of the code bases that I showed you earlier. For example, IIIA-CSIC, you can play around with this. Okay, so we've talked about multi-agent systems. Okay, there's this environment, there's these agents, they have actions and observations and so on. But what does it mean to do learning, multi-agent reinforcement learning in this environment? And that's basically summarized here in this one slide. Okay, so this is a modification of the basic reinforcement learning loop that you may have seen already if you studied single agent reinforcement learning with the Sutton and Bartle work. And here's just extended to multiple agents. Okay, so what's going on here? First, we have our environment at the bottom, which is just shown as a square. And then there's these agents, agent 1, 2, and so on until n agents. We're assuming there's a fixed number of n here, so they do not change. Every agent chooses certain actions. We call this then the joint action, all these actions taken together. They make some affect the state of the environment, something changes. And then in return, the agents get a new observation about the state of the environment, and they get a reward. Okay, so the observation could just be individually what they get to see. They may not see everything. They may just have their own local observation. And also their reward could be it's just an individual numerical, it's just a scalar number that is a proxy of the goodness of what they've just done. So in the easiest case, if they've done something that's good, they get a positive number, positive reward. And if they've done something that's bad, then get a negative number, okay? That's a proxy. But the real deal is that they don't actually care about just the immediate reward. In reinforcement learning, it's all about maximizing the sum of your rewards over time. So we call this the return. The return is the sum of the rewards over time. That's the actual thing that we're trying to optimize, because sometimes it's more important to maybe sacrifice near-term reward in order to open up opportunities for long-term higher returns, right? So it's all about strategic decision making. And in this loop here, you can see it goes on in a loop. So take action, something changes, new observations, new rewards, take action, and so on. And in this way, you are experiencing the environment over time. You're collecting data about what's happening over time in the environment. And with this data, with these experiences over time, you will learn. Okay, you will improve your policy and become better over time. That's the reinforcement learning training loop, but designed for multiple agents when there are multiple agents in the environment. I think this should be clear, right? Is this clear to everyone, or is this not clear to anyone? I think it should be clear, right? So it's pretty straightforward. Okay, so why do we care about MARL in the first place? Why do we not just say, okay, well, there's maybe these 3 robots, but I'm just going to use a single agent reinforcement learning algorithm and train a big fat policy that controls everyone at the same time, centralized policy. You could do this, but it doesn't actually work in many applications. So, okay, first let me tell you about this. There's 2 motivations I want to share with you. One is it may not be feasible to do a centralized single agent approach. For example, if we go back to the level-based foraging scenario that I showed you earlier with the 3 robots and the apples, in this case, if there's 3 robots and they all have 6 actions, then you see that the joint action space grows exponentially in the number of agents, 6 to the power of 3, 216. This already is the size of an action space that's already fairly difficult to tackle, even for the strongest state-of-the-art single agent algorithms. And if you add 1 more agent to this, 6 to the power of 4, it's not feasible anymore with existing single agent algorithms. So we need something to decompose the complexity of this control problem to make it more tractable. So what we could do instead is, why don't we just train 3 independent agents, 1 to control each of the 3 robots. Okay, so 3 robots, we have 3 agents. Now in this case, every agent only has to choose from 6 actions, not from 216. Okay, 6 actions is much more manageable. So now we have 3 agents that learn concurrently, and the added challenge, of course, is that they have to learn how to coordinate their actions. That's the new thing that comes in here. But in terms of the actual action space, it's much more feasible now, right? It's just much smaller. And that's, in a way, if you think about it, that's an instantiation of this computer science paradigm, which is to divide and conquer. Hands up if you know divide and conquer. I think probably everyone learned about this. It's the first thing you learn in computer science, right? And this is an example of divide and conquer. We're dividing a control problem into these multiple action spaces. But also there's some much harder reasons for why we need to do multi-agent reinforcement learning. And that's because in many applications, there's a hard requirement, that's what I mean by hard, to have decentralized decision-making. So we need independent, decoupled policies that can be deployed locally on the individual machines. There is no centralized entity that's able to coordinate them because of physical constraints or distances or other feasibility aspects. For example, in self-driving, it would not be practical to have a centralized entity that is relaying real-time actions constantly throughout the entire city. It would just not be practical. Hands up here again, yeah? I think there's a microphone here.
So just to understand that, you said that there are all decoupled agents for each of the multi-agents, but the whole goal of multi-agent systems is to also take into account the action of the other agents also, right? So
yes.
if that would be taken into account, won't it become similar to the single agent, like big space of agents, or?
No, because they have to learn in the presence of each other. And some approaches, they work by ignoring the other guys, they're just noise. Some approaches model the other guys, and that's what he's saying basically. But in all of these cases, the fact still remains that when they do get to choose an action, it's only 1 out of 6 actions, not 1 out of 216, which is a huge difference in terms of the branching factor, right? Basically, it's a multi-agent system. They learn together, they observe each other, they do have to interact, but it's about reducing their own control spaces, basically, and make
So
it.
it's like the output space is reduced, but the input space takes into account, of course, the actions of the other agents also.
If it depends on the algorithm, it depends on how you model the observations of the agents, but yes, ideally it should be something like that. Yeah. Okay. Going on. So the next thing I want to mention is we talked about multi-agent systems, multi-agent reinforcement learning, why we care about this. But actually, multi-agent reinforcement learning also comes with its own unique challenges. It's not just easy peasy applying multi-agent reinforcement learning. It does come with some pretty hard problems that have been around for decades now, and we still not particularly close to solving some of these challenges. It's very important to be aware of them. The one that's probably mentioned most commonly when we talk about problems with multi-agent reinforcement learning is this idea that the environment becomes non-stationary from the perspective of individual agents. Okay, every agent is learning; they're learning simultaneously, and that means, from the perspective of individual agents, things in the environment change because the policies of the other agents are a part of the environment. Okay, what they do affects the state of the environment, which affects my rewards and my actions. But if they keep changing, it means that the environment kind of keeps changing, and I have to track these changes and make sure that I converge neatly to a fixed point whilst the other ones are learning, and the other ones mutually have to do the same thing with me as well because I keep changing and they have to track me as well. So this non-stationarity is a pretty tough problem, and lots of research has gone into trying to tackle this. The other one is there's now a whole new range of questions, which is, what does it even mean to be optimal in a multi-agent system? In a single agent RL environment, we know what this means. We want to learn a policy that maximizes the expected return in all the states that we have. Okay, it's very straightforward. But in multi-agent reinforcement learning, that's not defined anymore because now what my returns are depends on what the other guys are doing. And we may have differences in terms of preferences, in terms of our own reward functions, in terms of the desirable objectives. So now there's a whole range of what's called solution concepts that define all kinds of different solutions for a multi-agent system. And some of them are more about fairness, some of them are about welfare, some of them are about exploitability. There's quite a few different concepts you can now think about. And there's not one right solution concept. It depends on your application. And you have to choose a solution concept, and it can become really complicated to learn these things. Another challenge is what's called the multi-agent credit assignment problem. I'll show you this in a second. But basically, the idea is now that the agents, when they observe what's going on in the environment, they now have to also disentangle everyone's contribution to the rewards that we've just seen. So was it my action that just gave me this reward, or was it this guy's action that just gave me this reward? And I have to see these things and kind of make these attributions as I'm learning. Turns out this is a really difficult problem. Scaling in the number of agents is very important as well. We want to be able to realize applications where there's maybe not just 2 or 3 agents, but maybe tens or hundreds of agents. So scaling is important. And these things are explored in the book, and we also explore them more in the upcoming lectures. I want to just visit 2 of them in a little bit more detail. The first one is this non-stationarity problem that I showed you earlier. So the idea is multiple agents are learning. The environment becomes non-stationary from the perspective of individual agents. And that means we have this moving target problem. Every agent is optimizing against the changing policies of the other agents. Right, so let's look at this image that I'm showing you here. This is a depiction of an actual learning process in the rock, paper, scissors game that I showed you earlier. Okay. Anyone not know what rock, paper, scissors is? I think everyone knows what it is, right? So, okay, I'm going to assume everyone knows what rock, paper, scissors is. So what does this show here? Here are 2 probability simplices, okay? Each point in a simplex here is a fully specified probability distribution over 3 outcomes. In this case, it's the rock, paper, scissors actions, right? So if I start in the middle here, where this, or let's say if I start here, then that is gives probability of 0.5 to the paper action and 0.3 to the rock action. Sorry, I think maybe this should be 3 here. I need to revisit this. But basically, there's an initial probability distribution. And what this line here shows is basically how these things are evolving over time for the blue player and for the green player. So you can see the probabilities keep changing. Okay, so there's training time. They train more and more and more. Same for the yellow guy up here as well. They're playing this game repeatedly with one another. And in this particular algorithm that we used here, they very smoothly converge to the center point here. And the center point is actually the unique Nash equilibrium solution of this game, which is when everyone plays all the three actions uniformly randomly. That's the unique Nash equilibrium that exists in this game here. So it's a concrete example of this book cover image that I explained earlier at the start, right? Where there's this learning process and they converge very beautifully to a center point, which is an actual solution. And in this case, they have successfully managed the non-stationarity by adapting to one another. But in many applications, if the algorithms are not well designed or the problem is just really hard to learn, this thing can be very chaotic and they go in all kinds of directions and they will never converge to anything because they keep chasing each other and it's very hard for them to understand what's going on in the environment, basically. This is an example where they have successfully managed the non-stationarity, but it could well be the case that it's just chaotic and they don't do this at all. Here's a one-slide description of this multi-agent credit assignment problem that I explained earlier. Let's go back to the level-based foraging example that I showed you earlier. This is the exact same scenario that I showed you earlier. And now let's say there's a time step T. All the agents perform the collect agent at the same action at the same time. And then they all receive a shared reward, which is +1, okay? So basically, someone was able to collect an apple. In this case, these guys here were able to successfully collect an apple. And as a result, let's just say in this case here, everyone gets a +1 reward because they're a team. They're doing a teamwork. So they now individually have to decide. They saw that everyone took the collect action. They saw what the state was before and what it is now. And they saw that they got a +1 reward. How do these different agents understand that this guy on the left here, this guy's action did not actually matter for the +1 reward because it was not able to achieve anything, right? The apple was too difficult here. It was these two guys who did the collect action at the same time. And only by doing this action in this state and at this time and at the same time were they able to get the positive reward. It's difficult for an agent to disentangle these attributions if that's all they get to see. And they have to do this repeatedly over time. So that's an example of a multi-agent credit assignment problem. Okay, so that's the part one, which is just a quick introduction to multi-agent systems, multi-agent reinforcement learning. Why do we care? What are some challenges? And in the next part, we'd be talking about some reinforcement learning basics. This is going to be a little bit more fast-paced. It's just some basics. I'm going to be skipping over some things. I'm going to just make sure we have some basic vocabulary. But I want to ask, who has some basic background in single agent tabular reinforcement learning? For example, you've done a course at university, you've implemented your own things. Hands up if you have a little bit of reinforcement learning. Okay, less than half. So I think we probably have to do this. Some of you may recognize a lot of this stuff already. Others may find it new and maybe a little bit fast-paced, but do go back to the lecture and to the course slides and also the book, and you can read this in your own time as well. So let's jump into reinforcement learning basics. Okay, so this is how we like to describe this. A reinforcement learning, basically, the algorithms learn solutions for sequential decision-making problems by repeated interaction in an environment. Okay, so there's a few things that need to be defined in this description. First of all, there's this term sequential decision problem. There's a process where we repeatedly take actions and then we repeatedly observe outcomes. That's a decision process. And there's a number of different models you can use. The most commonly used one is the MDP, the Markov decision process, but there's lots more complicated ones you can use as well. So in a reinforcement learning problem, that's the first thing you need to define. Your decision process, your model of the world, basically. How does the world work? And then the next thing you need to define is what does it mean to learn a solution? What is a solution, right? So the learning objective. In this case, it's pretty straightforward. In single agent reinforcement learning, in this case, it's just single agent. There's not multiple agents. It's typically called we want to maximize the return or the discounted return with a specific discount factor in each state. And that's all there is, basically. We want to learn a policy that is able to make choices so that over the longer term, we maximize the sum of the rewards. And basically, that's the goal. We're learning a policy for a particular decision process to learn a policy that is maximizing this objective, which is to maximize the expected discounted returns. Here's a graph description of this MDP model that I mentioned earlier, the Markov decision process. I'll tell you more about this in more detail in just a second, but let's look only at this graph for now. Okay, so there's a few different elements here. first there's the purple circles here, or blue, whatever. And this is the states at the different points in time. Okay, state at time t minus 1, state at time t, state at time t plus 1. This is the process that evolves over time. The state of the world changes over time. Then we have our actions, which are the red circles here. At each time step, in each particular state that we're in, we get to choose an action, okay? In this state t minus 1, we get to choose an action a t minus 1, which depends on that state. And then basically, depending on what state we were in and what action we've taken, we get a reward, which is this green circle here, a reward at that particular time step. So you can see how the arrows mark the dependencies. The action depends on the state, and the reward depends on the action and on the state, okay? And then the next state in return depends on the previous state and the action that we've taken. Okay, and so basically you go over this process repeatedly over time. Then this is the next state, and we get to choose an action again, which gives us a reward, and then the next state, and so on. That's basically how we go through this process. Formally, it looks like this. There's a number of components defined here. We have our state space S, which in this case is just to find a number of states. There's also a set of terminal states, which define what it means to finish this task. For example, in level-based foraging, when all the apples have been collected, finished, okay? Then there's a finite number of actions. In the level-based foraging example, it's just to walk up, down, left, or right, or to collect. Then there's the reward function. In this case, there's only one agent, so there's only one reward function, which is basically just a mapping from the state action and next state to a reward. Most of the time, there's only a mapping from the state and the action. We don't even, from of the current state, sorry. And then there's a state transition function, which defines the probabilities with which we move from one state to another state given a particular action, okay? And lastly, there's an initial state distribution, which defines what the first state is. Okay, you can just say there's always one particular state that we start in. That's a Markov decision process. There's a few different assumptions you need to be aware of here, and it gets a little bit more technical. Again, you can go back to the book if you want to absorb this in your time. The first one is called the Markov property. That's where this word comes from, Markov decision process. Markov property defines a type of stationarity, which means that the future states are independent of the past states and actions, given only the current state and the action that we're picking. Okay, so it's if you know the current state and the current action, then the past doesn't matter anymore for the future. Basically, we can ignore the past. That's what the Markov property means. And probabilistically, it looks like this. The probability of a particular successor state and a reward is independent of the entire past sequence, given only the current state and the current action. Another assumption in Markov decision processes is that we have full observability, which means that the agent gets to see everything. The agent gets to see the entire state of the MDP. In many practical applications, though, you would only see a little bit, right? You only have your own thing that you get to see. And there may be lots of things that you do not get to see. But in Markov decision processes, to keep it simple, we assume we get to observe the whole thing. And the environment is stationary. Okay, so the dynamics of the environment, which means the transition probabilities and the reward function, they will never change over time. They will always be like they were from the start. And lastly, in reinforcement learning in particular, we assume that we do not know the whole MDP. Okay, there will be many things in the MDP that we don't know. We may not know the action space. We typically do not know the transition function, the transition probabilities, or the reward function. But by the way, you don't have to take photos. All the slides are on the book website. You can get it all on the book website. Okay, yeah, good. All right, so these are some basic assumptions. There's probably more that are worth mentioning, but I'd say these 4 assumptions are probably the most important ones to be aware of. Here's an example for an MDP that we put in the book, okay? It's actually based on the reinforcement learning course that I teach at the University of Edinburgh, and it's kind of neat, so we used it in the book as well. So let's say here's an MDP, which is completely specified as a graph, similarly to the nodes that I showed you earlier, but this is a completely specified MDP. There is a start node. We always start in this start node, okay? And then in every node, there's different kinds of nodes. We get to choose certain actions. For example, in the start node, we can go left or right. If we go left, then there's a certain probability that we get into this node, which is side A. or there's a certain probability P that we get into a different node, which is that we have immobilized the robot. And basically, you can imagine that this is an example where you control a Mars rover. It has to navigate on Mars, and its goal is to arrive at the base node, the base station, basically, right? It's very simple. You could also just take a right action. Then there's a probability of 0.5 that you get to the base node, but there could also be a probability of, the alternative is that you get destroyed. You fall down a cliff or something, right? Similar, if you go left, there's a probability of 0.9 that you get to the side A, or there's a probability of 0.1 that you become immobile, like some kind of damage. And basically, the idea is that you learn an optimal policy that finds, on average, the ideal sequence of actions to maximize the probability of getting into the base. In fact, it's not actually to maximize the probability of getting there, it's to maximize the returns, which is the sum of the rewards that we collect over time. Okay, this was just a basic MDP example for a toy problem, the Mars rover. Right, so now we're getting into reinforcement learning in an MDP like this. We have the MDP specified, which is our world. This is, for example, the Mars rover. And now we want to learn in this environment. So we get to see this reinforcement learning loop that I showed you earlier, but just for a single agent. There's our environment, which is the MDP, and there's an agent which exists in the environment, gets to pick actions, changes the state of the environment, and then you observe something new and you get a reward. And you learn in this loop by collecting data over time, and you become better over time if you know how to learn. There's two main categories of reinforcement learning algorithms that are often that you learn about. One is value-based reinforcement learning. This is when you actually learn value functions that assign estimates of discounted expected returns to the individual actions you can take. And then you derive a policy that uses that to choose optimal actions. And then in contrast to that, there's also this policy-based RL. These types of algorithms learn to optimize policy functions directly. Okay, so if you have a function for your policy, there will be certain parameters. For example, in deep learning, you have your deep network, and these are the parameters. And you directly learn to modify the parameters rather than indirectly learning to estimate the values here. So these are the two main categories that you also still see in multi-agent reinforcement learning. And basically, over the next few slides, I'm going to tell you a bit more technically what these returns are and give you some examples of these two classes of learning algorithms for value-based and for policy-based. And that's as far as we go, basically, right? I'll skip over some details. I'll just make sure that you have seen these basic ideas before we go into the next part. Right, so first, what are discounted returns or expected discounted returns? In reinforcement learning, we want to learn a policy that maximizes the expected return. In this case, we're going to be using lowercase u for a return. And the return, as I mentioned earlier, is just the sum of the rewards, okay, over time. One thing you need to keep in mind is that if the MDP is non-terminating, which means it goes on and on and on and on, there's a problem that your return might become infinite. And then the problem is not defined anymore. You cannot solve that kind of problem. So what we then do is we add a discount factor, which is gamma here. Gamma is basically discounting the reward at each time point. And it means that by doing this is a geometric series which has a fixed point, and then your return becomes defined. It's a finite number again, guaranteed to be finite even if the MDP goes on indefinitely. So that's a little sort of trick that we use in reinforcement learning to make sure that the returns are finite. There's also other motivation which we described in the book. It's not just about the fact that MDPs could be infinite. It's also about modeling termination probabilities, but I'm just going to leave it at that for simplicity. Okay, so that's a discounted return. And basically, we care about the expected discounted return. That's why there's an expectation here, because the environment is stochastic. The effects of our actions could be stochastic, which means sometimes they work, sometimes they don't work. In the Mars rover example that I showed you, you saw that in some cases there's probabilities that we go left or right, depending on the different actions. So that's why we maximize the expectation of our return, because we cannot fully control the environment. There will be these random effects always. Right, so now we get into closer to this value-based approaches. We can learn something called a state value function, which is v pi s. So this is the value v assigned to a particular state s under our current policy pi. Our policy pi is the thing that chooses the actions in the different states. And it's defined like this. The value v for a particular state s under a policy pi is just the expected discounted return in that particular state, and then moving forward from that point onward. Okay, following that policy from that point onward in that state, you sum up those rewards, that's your return there. The expectation of that is the value. It's as simple as that. Okay, value is just expected return. You can actually define this recursively, so you understand that if you write this out, you spell this out, the sum basically, reward at time t, and then you discount the subsequent rewards, and then time t plus 1, and so on. You can write this down as a recursion where the return is defined as the immediate reward plus the discounted return for the next state. That's what this means. And this recursion is important because a lot of the value-based approximations are actually recursive. We'll see this in a second. But basically, therefore, the value at the particular state S is just the expectation of this recursive definition here, the reward in the next time step plus the discounted return in the successor state. Everything clear so far? Should be clear, right? I think it's pretty straightforward. Okay, so now we get into one of the most important, most central ideas in the entire world of reinforcement learning, which is the Bellman optimality equations. Okay, named after Richard Bellman, who was at his time one of the first people to actually develop this rigorously, and he published a book from 1950 something, I think, which is called I think it's called Dynamic Programming. So it's widely cited, very technical book where he explains these ideas. And he even talks about games at the time already, far ahead of everyone else, lots of other people. Okay, so basically, the Bellman equation looks like this. If we start at the top here, this is just a copy and paste from the last slide where we have the expected return defined as this recursion here. We can actually spell this out. Okay, we can spell this out by doing various sums, various margins. Okay, so how do we spell this out, this expectation here? Sorry. It looks like this. First, in a particular state, that's where we're starting, we get to choose a particular number of actions. Let's say 6 actions, like in level-based foraging. So we're summing over the different possible actions that we get to pick. Every action has a certain probability that we give to the action based on our current policy, right? So this is our policy pi, the probability that it gives to that action given the particular state S that we're in. And then you move further inward into the sum by summing over the possible successor states, S prime, okay? What are the possible successor states that could happen after that? So we need to sum over those. We attach probabilities to those different successor states using the state transition probability function that we defined. And then we multiply this by the immediate reward that we receive by making this transition from state S to state S prime, given the particular action. And we then add to that a discounted expected return of the return in the successor state. Keep going forward with this clicker, sorry about that. And basically, the last step at the end here, this expectation, if you look closely, well, that's just another application of our value function in the successor state. And now we have a closed form recursive definition of this entire expected return here, right? So this function here that we care about can be spelled out using sums analytically exactly as shown here. And in fact, this defines a linear equation system that you can solve with Gauss elimination and other classical approaches that you learned about in first year university or something. So that's beautiful, right? If you think about it, this is a nice analytical closed form solution that you can solve exactly to a fixed point with existing approaches like Gauss elimination. But of course, here we don't want to do Gauss elimination. We want to do reinforcement learning. So it's a different way to solve this. Right, so another idea to do this is to, rather than attributing values to states, you can also attribute values to combinations of states and actions. That's the other concept that you often see, Q. In fact, probably the by far most famous reinforcement learning algorithm called Q-learning. Everyone knows about Q-learning. It's the first thing you learn. It's actually named Q-learning because it learns this Q function. It learns to assign values to states and actions. You'll see Q-learning in just a second. But basically, it's very similarly defined. Rather than just having a function V for states, we now have a function Q for combinations of states and actions. And that is simply the expected return given the particular current state and executing that particular action in that state, and then subsequently following our policy pi in the next states. So it's almost the same definition, except that we add the part at the end here where we also add a particular action that we want to execute. And as before, we can spell this out as a Bellman equation, right? We spell this out by doing the sums over actions, and the sums over successor states. And then at the end, we make a closed form by just doing the Q. Oh, sorry, I think this should be V here. Okay, I just found a bug in the slides. I'm going to have to make a note of this and fix that. Yeah, at the end, this should be V here. So I want to make a note, make sure I don't forget about fixing this. Slide 22. Okay. Yeah, sorry about that. I'll fix that first thing later. Yes? Oh, you're right. I need to go back to this. Yeah, this is actually a copy and paste from, that's why it's incorrect. It's copy and pasted from the V function definition. Yeah, thanks for letting me know. I need to go back to this copy and paste mistake. But I think you can kind of close the loop there mentally yourself. And I'll fix this later as I get home. By the way, if you guys end up looking at the slides and you find anything else that doesn't make sense or typos, please let me know because we're still polishing the slides. We want to make sure they're as good as possible. All right, so we've got the value function, which is a value assigned to a particular state in action. This is the Q function. And now we can have a policy that acts greedily with respect to a value function. And basically, that's the thing that we're trying to learn, right? We want to learn an optimal value function, which assigns the optimal unique expected returns to the different states. And then we just want to have a policy that is greedy with particular value function, which means that in any particular state that we're given, we choose an action that maximizes the expected return in that particular state under our value assignments that we have in this case. So it looks like at the bottom here, if we have the Q function in a particular state S, our function pi assigns maximum probability to the action that maximizes, that has highest Q value in this particular state. And if it's more than just one action, which could be the case, then you can have arbitrary probability assignments, or you can just pick one of those and assign all probability to that. But the values for the optimal Q function will always be unique. So we'll see this in a second there. Okay, now we get to that already mentioned. So we have a greedy policy with respect to a Q function. And we say that a greedy policy with respect to a value function is optimal only when using the optimal value function. And the interesting thing about MDPs is that there's always a unique, only one optimal state or Q value function, but there might be multiple optimal policies because, for example, if you have a state where multiple actions have maximum Q value, then you can pick any of them. So there could be an infinite variety. But every MDP is always uniquely solved with one unique optimal Q function. And that makes them really interesting in terms of a mathematical object that we can actually solve. So the optimal value function for an MDP is defined like this. We use the star asterisk to define optimality. So now we replace the pi here with star, which means under an optimal policy, the value of that particular state is the same as the value that you can maximally achieve in that particular state. So that's what the maximizer goes over. Any policy that maximizes the value in that particular state. And the value, remember, is the expected discounted return. Similarly, for the Q function, Q star is now the optimal Q function, which is also unique. And in this case, it's also a policy that maximizes the Q function subsequently after taking the action A in that state. Okay, so therefore the optimal policy is pi star, which for a given unique optimal Q function, Q star, always chooses the maximum value action in that particular state S that you're giving into the policy function. So that's basically it. That's the object mathematically defined that we're trying to learn in a given MDP. This pi star is what we're trying to learn. And reinforcement learning is basically a way to learn this pi star through time by repeatedly interacting in the environment. All right, so now we looked at value functions, V values and Q values. V values assign values to states, Q values assign values to actions and states. And now we're going to look at some algorithms that try and learn these value functions, okay, whether it's Q or V. And the first thing you tend to learn when you get into reinforcement learning is what's called dynamic programming. Dynamic programming is this thing that people like Richard Bellman developed before reinforcement learning came out. But reinforcement learning relies heavily on these ideas that were developed in dynamic programming. Okay, so what is dynamic programming? Dynamic programming, or DP, is a family of algorithms to compute optimal value functions and optimal policies and MDPs, okay? The thing that I just showed you with the V star or the Q star, this is the thing that we're trying to learn with dynamic programming. And once we have V star or Q star, then you just saw that we can derive optimal policies from those optimal value functions by greedily picking actions from V or Q. In dynamic programming, we assume that we have compute knowledge of the MDP. So if you remember how an MDP is defined, we have our state space, we have our action space, we have our state transition probabilities, reward function, and so on. Everything there is to know, we know about the MDP. That's the assumption in dynamic programming. And basically, the way it works is, given this compute knowledge, we use ideas like the Bellman equation as in an operational way to find these optimal value functions, basically by iterating and repeatedly applying these Bellman equations. So here's a starting point. This is basically this is probably the most well-known type of dynamic programming algorithm that we learn about. It's called policy iteration. And policy iteration is a dynamic programming algorithm that alternates between two steps. The first step is policy evaluation. This is when we compute a value function for a particular current policy pi. Okay, so we have a current function pi that assigns probabilities to actions in states, anything that you give to me. And then we want to approximate this associated V value function for that particular policy function pi. Okay, that's the policy evaluation step. We say evaluate because the values is the thing that we want to now learn from a particular policy. Once we have done the policy evaluation, then the next step is the policy improvement. And that is when we then use our estimate of this value function in order to make certain improvements to the current policy that we have. Okay? Typically, this means that we greedify the policy with respect to the value function that we just computed. And sequentially, it looks like this. If it's a well-defined algorithm, which these algorithms are, then in the process, we start with an initial policy pi 0. Then we learn the associated value function for that particular policy pi 0. We make an update to the policy. It's now pi 1. We learn the value function for that particular policy pi 1. And then we make an update based on that and so on. And we repeatedly apply these updates until we eventually converge to the optimal unique value function V star. And from that, we can derive the optimal policy pi star. That is basically this process, how you can imagine, will work out over time. In practice, we would typically terminate this learning ahead of time. So for example, if there's a threshold for things that have changed, if there's only very small things that have changed in one iteration, then we can also already terminate. That's typically how it's done in practice. So let's look at a pseudocode. This is a complete pseudocode for a policy iteration algorithm. And I'm going to walk with you through this step by step. Okay, so first we initialize the policy randomly. Let's just say initially the policy gives uniform probability to all the actions that we earn, okay? And then we also initialize the value arbitrarily. For example, that could just be 0 initially. The whole value function could be 0, and the policy could initially just be random. Okay, that's just how we start. And then we repeat in our learning. First, we do our policy evaluation. This is the first step. And here, the way we do this is by repeatedly applying this function that you saw earlier. This is the Bellman equation for the value function. And it turns out that we can repeatedly apply this to learn successively the value function here, VS, sorry. We do this until we converge for all the states that we're in. Convergence could be that we have no changes anymore in the estimates or just a small delta, basically. And then we move into the policy improvement step. We've just estimated a particular value function V, and we use that to improve our policy. Okay, how does it work in the pseudocode? First, we have a bool variable here, which is true. Is the policy stable, yes or no? Let's say yes initially. And then we iterate over all the possible states that we're in. We choose an action from the current policy, and then we see what the policy would do greedily with respect to the value function that we've just computed. And if those things differ, then we need to change basically the policy is not stable because we need to change it now to the new greedy action. So the policy is the policy is not stable anymore. Things have changed, and basically that. Hold on a sec. Is there a typo here? No, yeah, it makes sense. Checks out. So that's basically in a nutshell, the policy iteration algorithm where we have these two steps: policy evaluation and policy improvement. And over time, as we repeat those steps, you converge to the unique optimal value function. And then from that, you have your policy that you can extract. Okay, there's one more algorithm in dynamic programming that I'm going to show you, and then I'll leave it at that. That's as much as I'm going to tell you. This is value iteration, which is an even simpler algorithm. Value iteration just uses one particular equation. So rather than doing these whole steps that you just saw with policy evaluation and policy iteration, we're going to just do this one equation. And this is basically an application of the Bellman optimality equation, where we successively learn a value function, case k to k plus 1 and k plus 2 and so on, by maximizing, choosing the maximizer action over the current expected return equation that you saw earlier. So we repeatedly apply this function over the entire state space S basically, and that already is already defined and gives you in the limit the unique Q values, state values. So it's a very simple dynamic programming algorithm that just takes 3 or 4 lines of code to implement, as you see here in this pseudocode. But I'm going to skip over this. You already saw the other pseudocode. Okay, so that's dynamic programming, and no one uses dynamic programming in real applications, right? It doesn't scale. We cannot iterate over entire state space. It's impossible. We have environments where there's billions of states. And also, it's not practical. We cannot assume that we have all this knowledge. In practice, we don't know the transition function. We don't know all the state spaces. We may not even be able to enumerate over the entire action space, not even that. So now we're going to move into reinforcement learning. Reinforcement learning instead tries to learn these value functions and policies by experiencing the environment, by trying actions, by seeing the outcome of the actions, and observing these experiences and learning over time, basically. And the main idea, probably the single most important idea that defines the entire field of reinforcement learning, I think you could really say this, is temporal difference learning, TD learning. Effectively, almost all reinforcement learning algorithms, including the ones that we do now in deep learning, are in this temporal difference learning family. And temporal difference learning itself relies on these dynamic programming ideas. So in the book, it's explained in more detail, but I just wanted to basically spell out this connection that temporal difference learning uses some of these ideas from dynamic programming. Okay, TD learning, temporal difference learning, is a family of reinforcement learning algorithms that learn optimal policies and value functions based on data collected in the environment by trying out actions. Okay, so there's this trial and error effect. We try, we see what's happening, sometimes good, sometimes not so good. And the important thing about dynamic temporal difference learning is that we do not assume that we know these elements. We do not know the full MDP. Instead, we just try out actions and we get to see the outcomes. So it's more practical in a sense, right? So what is a temporal difference learning update? Again, our main mathematical objectives that we're trying to learn is this value function, V, which assigns a value to a particular state. But now we're doing this by learning and trying out actions in the environment. Basically the main update rule that you get to see in these temporal difference learning algorithms is a version of this here. This is a one-line description of the update rule. Basically, we update the estimate for a current state value by using the current estimate that we have, but we're adjusting it a little bit. And in fact, we're adjusting it by this learning parameter called alpha. This could be a small number. In practice, this would be a very small number typically. And in practice, you would also usually change this over time so that it becomes smaller and smaller. It has to do with learning stability. But basically, then instead, there's this important thing, which is this char here. This can be instantiated in a number of different ways. And I'm going to show you just 2 examples of how to instantiate this in these slides here. But there's many more ways you can do this. Okay. Similarly, if instead of learning the state value functions, you learn directly the state action value functions, which is this Q function, it looks very similarly. Okay, so here, I think I forgot the key here. Need to make a note of that. Slide 31. Okay, yeah, there's a Q missing here. Should be just a Q here. Similarly to above here, you need to you adjust your current estimate by moving a little bit into a new estimate, which is defined by alpha and the char here. Okay, so this is almost the same as up here, except that it's for a particular action and state combination. So this thing here, we call this the update target because we're moving towards that target defined by a step size, which is alpha, or the learning rate. Step size and the learning rate are two common words for it. Right, so the first algorithm that we're going to look at is SARSA. This is one of the most basic algorithms that you learn about. SARSA is called SARSA because these letters S-A-R-S-A, they simply correspond to an experience tuple, which is the current state, the action that we take, the reward that we get, the next state that we observe, and the next action that we do in that state. SARSA. Okay, that's where the name comes from. It doesn't have any other deeper meaning, basically. But in this case, here's the experience tuple that I just told you about, which makes up this name SARSA. And here the update target looks like this. Okay, it's the immediate reward that we receive after executing that action in that particular state. And then we add to that a discounted Q value for the next action that we take in the next state. That defines the entire update rule for this algorithm. This basically, if you take this definition of the update target and you go back to this slide here and you plug it in here, then, you plug it in here, then that's already your full definition of the SARSA learning algorithm. Okay, then that's basically the entire algorithm, and you can already go ahead and implement that and learn your V functions. Okay, so if you look at this, it looks similarly to the Bellman equation that we saw earlier, right? So we defined V or Q by spelling out these different sums over the actions and over the successor states. And in this case, it's the closed form Bellman equation for the state action values, or the Q function. And if you look at this here, the red blocks here, it's kind of a correspondence to what we have up here. The immediate reward is that here, the RT. And then we did take the discounted Q function for the successor state and then the successor action that we pick under our current policy. This is the thing up here. So that shows the connection of temporal difference learning with dynamic programming. Down here is a classical dynamic programming approach, which is closed form and requires that we do these complete sums over all the actions and all the successor states, and we need to know the dynamics. Instead, up here, we apply this only once for only one particular state action combination, one particular reward that we got, and one particular successor state and successor action. This is our experience tuple. And it's basically a stochastic approximation that just samples this learning update just once using our experiences. So you can see it's very nicely derived from the dynamic programming family, but it doesn't require that we have all this knowledge, and it doesn't require that we do all these sums down here, which are very hard to do in practice. So ultimately, the update rule for SARSA becomes this. You can plug in the update target here, and you can spell it out, and so it looks like this. This thing here is called the update target. The whole thing here is called the TD error because it's the difference between the new estimate and the old estimate, just in terms of terminology. Another important piece of terminology that you often see in reinforcement learning and you need to be aware of is bootstrapping. Hands up if you know what bootstrapping is. Okay, what's bootstrapping?
Probably you will explain it better,
Yeah.
but we sample the actual states and action and use it to reinforce the Q function that we have. We sample, we update it. Not quite?
Kind of getting there, but not quite. Let me explain, but I think you're getting there. Bootstrapping is actually simpler. Bootstrapping just means it's a statistical concept, not just in reinforcement learning, but in the whole statistics. It means making estimates, statistical estimates, by using other estimates. That's all there is. So we're bootstrapping off of existing estimates that come from other parts of the environment to make estimates here. So the way it's shown here is that we have our old estimate here that we're trying to update, and we use our old estimate and also other estimates from other areas for these other states. And that's what's called bootstrapping. It's very important because you see this a lot in reinforcement learning. Bootstrapping is one of the core ideas. Okay, so here's everything spelled out as pseudocode. I think I'm going to leave this here because there's another piece of pseudocode that I'm going to get to in just a second. There's also a piece of mathematics which shows that this SARSIC learning algorithm is actually well defined in the sense that under certain assumptions, which are statistical assumptions, you actually have an algorithm that in the limit will learn the optimal unique value functions and based on that also the optimal policy function. So basically there's two assumptions you need to have. One is that all state action pairs are explored infinitely many times in the environment, and there's ways in which you can ensure this theoretically by having always non-zero probabilities assigned to all the actions. And the other assumption is this standard stochastic approximation conditions, which is basically two assumptions. And basically this just means that the learning rate will change over time so that it's never overwhelming, basically, the updates. It's basically a geometric series, which is defined by the second part here. But it's a bit technical. I'm going to leave it at that. Just what you can take away from that is that there are certain assumptions, and under these assumptions, these algorithms have a beautiful piece of theory that show that in the limit, they converge to these optimal value functions purely by this process of trying out actions and learning over time what's happening. Okay, I mentioned earlier there's this assumption that we need to explore all state actions infinitely many times, but the problem is if you have a fully greedy policy, you always pick one action, always, the greedy action. And so that would violate this convergence condition. Instead, we need to have probabilities that are never, we need to have a policy that always assigns non-zero probability to all the available actions. And that's what's called an epsilon greedy policy. So rather than giving all the probability to the maximum value action, you now have a parameter called epsilon, which is between 0 and 1. And that basically defines a probability with which we would choose, instead of the greedy action, we choose a uniform random action. Okay, so that there will always be a probability that we give to all the actions. And basically, it's summarized here. I'm going to move on to the next part now. This is probably the single most important learning algorithm in the entire field of reinforcement learning. And a lot of new algorithms still refer to this because the ideas are very closely related. So it's called Q-learning. In fact, Chris Watkins and Peter Dayan also, he did his PhD in our school at the time. In fact, quite a few people, for example, who knows Jeff Hinton? Jeff Hinton got the Turing Award recently for his backpropagation algorithm that drives all of deep learning. Jeff Hinton also did his PhD in our school and some other guys like that. So there's a lot of history in that area. But basically, just a tangent. Q-learning is a very popular TD learning algorithm, and it's even simpler than SARSA, where I just showed you. The difference is that we're now basically using the Bellman optimality equation. You're going to see this in a second. There is a maximum operator, and we learn the optimal state action value function directly. So how does it look? We're going back to this idea that we need to define an update target. This is the thing that you saw earlier that we have to define. And now it looks like this. It's even simpler than what we had before. The update target is defined as the immediate reward, RT, plus applying one discounting over the maximizer action and the Q function for the successor state. Okay, so we're taking the max action, A prime, in the successor state, T plus 1. And that defines the entire update target. Reward plus gamma times the maximizer in the Q function for the successor function here. Again, we take that whole update target, we plug it into the update rule, and then it gives us the entire Q-learning update rule, which looks like this. This is, in a one line, defines the entire Q-learning algorithm. And the difference is now, compared to SARSA, that we have a maximizer here, so it becomes non-linear here. And we basically, we do not need to sample our actions in the successor state anymore, so it can use fewer experiences. All right, so let's go through this pseudocode, and that's the last pseudocode I'm going to go through with you for this part of the lecture. So Q-learning, let's see how this works in practice. Going through this step by step. First, we need to initialize the Q function. For every state and action that we can combine, let's just say we give it a value of 0. But it could, in fact, be arbitrary. Let's say it's just 0 for simplicity. In fact, the only thing that cannot be arbitrary is that if there's terminal states, but it's not shown here. So for simplicity, let's just say 0. Then we're going to do our learning, okay? We do multiple episodes. Each episode starts at time 0 and then resets the MDP. So it's our initial state. That's how every episode starts. And then we have our time steps. Okay, T is 0, 1, 2, 3, 4, 5, and so on until you terminate or until you have used your time step budget. In every time step t, we get to observe the current state S. Remember that in MDPs, we assume that we observe the full thing, so we know what the current state S is. And then we have an epsilon greedy policy, which means with probability epsilon, we're going to choose a random action. We need to pick this probability epsilon. For example, it could be 0.05, 5% chance. Or otherwise, we pick the greedy action, which is the one that maximizes the current Q value for that particular state. Okay? Those two lines here define our policy. And then we apply this particular action that we just sampled. We observe the rewards that we get after executing that action. And then we observe the successor state S plus. Okay? And now with this experience, with this data that we have here, the current state, the action that we picked, the reward, and the successor state, that's all we need to apply one time this Q-learning update rule that we just saw earlier in the slide earlier. Okay? So we update our value estimate at this particular state with this particular action by modifying the current estimate, by moving it by alpha into the direction of this TD error here, or this particular TD update here. Okay? Is this clear for everyone, or is there any questions here? It's a pretty straightforward, small algorithm, right? Question there?
So this is basically applicable to only discrete states, right? Or discrete problems,
Yes.
not to continuous problems.
Yes. Because in our example, we defined finite MDPs where everything is discrete and finite.
Okay. Thanks.
Yeah. Any other questions, or is it clear for people? The pseudocode, pretty straightforward, right? You can imagine how you can write this down in your Python script. It's just a few lines of code. And the nice thing is, under these assumptions that I showed you earlier, you visit your actions infinitely many times, at least in theory, and you have your stochastic approximation conditions, which is a condition on the alpha. This algorithm is guaranteed in the limit to learn the optimal unique value function of the MDP. And when you have that, you also know what the optimal policy is, which is just the policy that always picks the maximum value action in any given state S. That's it, right? That's very simple, but very neat. Okay, so last slide, I think, for this part of the lecture. There's now this question of how to evaluate algorithms. Okay, so you implement your MDP, for example, the master over MDP that I showed you earlier. There's the states and the probabilities for how the states change and so on. Then you implement the algorithm, Q-learning, for example. You just saw the pseudocode. Okay, you initialize, you run through your learning, your episodes, you collect the data, you apply your update rules, and you want to see what's going on. Okay, you want to plot some results and evaluate whether or not we learn something. So there's a few things you can do, but this is basically the most common way to do this. Here's a few evaluation plots which show a bunch of different algorithms. Let's just look at this one here for simplicity for now. In this case, let's first look at the axes. On the x-axis, you have your environment time steps. You start with 0, and then you go 100, 200, 300 times, 400 times. This is the number of time steps t that you accumulate over time, okay? In fact, some people would plot the episodes here, but I think we should all be plotting the environment time steps. That's actually the standard now in deep reinforcement learning because different episodes may have different length, okay? Sometimes an episode may finish earlier, and sometimes an episode may be longer. And then if you plot your episodes here, it may actually not show the actual amount of training data. So the showing actual training time steps across episodes, this could be many episodes here, is the most appropriate way to show your amount of training data. Okay, so in this case here, by 500, you have 500 experience tuples. This is the amount of training time. And then we have our y-axis, which is the evaluation returns. Returns, you know what this is already. This is the sum of the rewards that you accumulate in an episode. And in fact, we call this something particular here. We call this evaluation return. And the reason why we call it that is because there's something else called training returns as well. The training returns are the returns that you get in your episodes as you execute these pseudocode here, okay? But in this case, we still have our epsilon greedy policy. After training, though, when you have your unique value function that you've learned, you do not want to do this randomization anymore because there's no point. You don't need to learn anymore. You don't need to collect data anymore. This is not needed anymore. We only do this. And that's what the evaluation returns mean, because when we evaluate the actual policy that we end up deploying, it has no randomization anymore in the policy and gives you reflects the actual discounted returns that you would get. And what you can see here is two algorithms. Orange is for Q-learning. Blue is for SARSA. You have your corresponding lines here. And you can see that both of these algorithms for this simple example in the Mars rover, you can see that we fairly quickly learn to do the optimal, learn to solve learn the optimal unique value function and then correspondingly the optimal actions. The horizontal dashed line here shows you the just as a for comparison the actual unique value in the initial state, which is 4.1. So you can see that we actually successfully learn a policy that executes the optimal sequence of actions in the initial state. That's why we're overlapping with this horizontal dashed line. There's a few more plots here. You can see down here, for example, in the lower left, we only show lines for Q-learning, but we use different learning rates, different values for alpha. For example, alpha 0.01, 0.03, and so on. And you can see that the different learning rates have a big impact on the actual ability to learn the optimal policy. For example, it turns out that if you use a learning value of, what is it? Here, 1 over the K, I think is it the episode number? I need to check this again. But basically, it decreases over time. And that is basically implements the stochastic conditions that I showed you earlier. We learn very quickly. But if we use instead a learning rate of, say, the blue line, which is just a constant 0.01, you see that the learning is much less efficient. And in fact, we're actually plateauing here. We will never reach the dashed line at the top there. So you can see the fact that we have a constant here is actually violating the condition. And in this case, the constant was too small, basically. It was not able to actually collect enough data to converge to the optimal line up here. So what this means for you is that this hyperparameter or the learning rate is a very important part of this learning algorithm and needs to be tuned very carefully. And this is still a problem in reinforcement learning. Okay, this is some of the simplest, oldest, most basic stuff. It was already a problem then. And today, in the most sophisticated, super duper state-of-the-art deep reinforcement learning algorithms, we have the same problem still, which is that we need to very carefully tune these hyperparameters. Except today, everything is much more difficult to tune because we have very big networks, we have very big problems, and we have it's very expensive to run these learning algorithms. And so tuning these hyperparameters, in addition to many other hyperparameters, is one of the dark magic, I would say, one of the sort of most engineering-heavy aspects in reinforcement learning if you want to make it practical. So it's you can tell from that there's certain things in reinforcement learning that seem to be just implicitly kind of hard. After decades of research, we are still not smarter than this, basically just trying out different alpha values and seeing what the best is. We're still there. We're still doing it like that. Okay, that was just the end of this part of the lecture. We have covered in an introduction into multi-agent systems, what's multi-agent reinforcement learning. We have talked about some single-agent basics in reinforcement learning, for example, Markov decision processes, value functions, dynamic programming, and then temporal difference learning like SARSA and Q-learning. And I think we're going to take a break from here. We're going to do some questions and then take a break. And then in the next part of the lecture for today, we're going to be talking about games, which is our first step into the multi-agent part. But before we go into the break, I just want to see if there's any questions here or online about any of the things that we covered so far. Any questions? Don't be shy, right? Any questions you have? First question there, yeah. And I think we had microphones, yes.
For the example of multi-agent reinforcement learning that you showed, you were using a single reward that some agents need to disentangle. I imagine there are certain situations where agents would have different rewards functions. So
Yeah.
I assume that's not the only case, and there are vectors of rewards, I guess.
Absolutely, yes. That was just what's called a common reward. There's only one reward, everyone has the same thing. And that's already kind of difficult for this reason that I showed you. But in many really interesting applications, as you say, it would not be the case. And in fact, that's what we're going to be talking about in the next part of the lecture, which is these different, how you can define these games and how agents may have different reward functions. Sometimes these reward functions might be a little bit similar. Sometimes they might be completely opposed. Like if they're playing a game of chess, you're my enemy, right? Basically, so completely opposed reward functions. And then it becomes really tricky to define what optimality is. So really rich space.
So about the reward, the credit assignment problem, do we still have the credit assignment problem when we're in a competitive setting, or?
Yes, definitely, for sure. That does not affect that problem. In fact, there's actually two types of credit assignment problem. So the first credit assignment problem, before we even go to multi-agent, is inherited from the single agent RL problem, and that's called temporal credit assignment. So temporal credit assignment means, let's say I take a bunch of actions, action, and I see certain rewards at the end, okay? Now the question is, which of these past actions were actually important? Which of these past actions were needed in order to get this reward that I just got, and which of those were not needed? Like, this is temporal credit assignment, over time, temporal. And now this still exists in multi-agent reinforcement learning. And now we also have the lateral version of this, which is whose actions contributed to the reward. Not just which of the past actions, but actually whose actions. Because we're all taking these actions simultaneously, and some of them may have an impact on the actual rewards that the agents received. But whether or not we are in opposition or how these rewards are defined does not affect whether or not this problem exists. The problem always exists. It sometimes can just be more pronounced than in other times. For example, when I showed you earlier the example where there's only a +1 reward that everyone gets, then it becomes really tricky for people agents to disentangle the contribution of individual agents' actions. But even that is still the case if one agent gets a +1 and the other agent gets, for example, a 0. Because for that 0 agent, it's still not clear why it got 0 and not 1, right? It still has to learn that it got 0 not because of this guy's action, but because of its own action, right? So it still exists.
Thank you.
Any more? I think there were more here, yes.
So just on slide 15, I had a question.
Okay. You want me to go back to slide 15? Yeah. Okay.
It's a graph. So I was just curious why there is an arrow going back from the state in the current time point to the reward in the previous time point. So what's the dependency?
Maybe let's look at this one. We're only caring about the graph, right? So which arrow?
So there's this arrow from state ST going back to RT-1. So is the reward in the previous time point?
Yes, because the most general definition of the reward function is actually a mapping from the current state and action and successor state. And in fact, in many practical applications, the mapping really is just this arrow and not the other arrows. Basically just depends on what current state you ended up in. This is the most general way to define a reward function, but in practice, you may end up having a reward function that only depends on this or only depends on these two things. But the most general one basically allows you to represent any one of these kinds of definitions that you can come up with, including any of these subsets. Does that answer the question, or?
So I am a bit confused. How does it affect the reward at the previous time point, the current state? Because
no, yeah, that's just a terminology. So basically, this is the state that we're in now, but we're using RT-1 for the reward that we got getting into the state. It's just a terminology. Other, for example, a Rich Sutton reinforcement learning book that people have used for a long time, they actually use a different terminology where this is then RT, not T-1. But for various theoretical reasons, we decided to go with this terminology. Does that clear up? It's just a notation aspect, I think.
Okay, all right.
Basically just means this is the reward that we get once we move into the current state ST. You could, if it makes it easier mentally for you, you can just change the notation here and use a different notation, which would be RT. Maybe then it looks more logical to you, yes. But there's other reasons why we haven't done that, which are in the book, basically.
Okay, I see. And a second question, what would be like a situation where Q-learning would be used over SARSA?
A situation where Q-learning would be used over SARSA. Okay, one is SARSA, there's some things that we haven't covered here, okay? I didn't tell you the whole story, but there's more to it. There's an idea called off-policy and on-policy reinforcement learning. SARSA is an on-policy reinforcement learning algorithm because it always uses only data to learn that comes from its current policy that it's executing on the policy, on policy. Q-learning is an off-policy algorithm because in the learning update that you saw, we have a max operator, which means that in the target that it's computing, it actually uses basically an estimate for the maximum action in the successor state, which is never actually executed. That's why it's called off-policy. And the reason why I mention this is because off-policy and on-policy algorithms have different trade-off profiles. For example, Q-learning tends to be much more efficient than SARSA because of this off-policy nature. SARSA, though, on the other hand, tends to be more stable than Q-learning because of the on-policy nature makes certain theoretical properties easier to satisfy, basically. So there are certain theoretical reasons why you might prefer one or the other, but in practice, off-policy algorithms tend to be much more efficient. And in fact, today's state-of-the-art reinforcement learning algorithms tend to be primarily off-policy algorithms for this efficiency reason. It means that you can reuse a lot of data that comes not from the current policy, basically.
Thank you.
More questions?
So you said that there is only one optimal Q star, but there can be different policies that can lead to this Q star. So does that mean that all these different policies that can lead to Q star is an optimal policy?
Yes.
Okay.
So let me give you an example. Let's say we're in a current state, and let's say we have 3 actions. And let's say the optimal unique Q value function gives value 5 to 2 actions and value 0 to one other action. So we know this one other action with 0 we're never going to take, right? It's not optimal. The other 2 guys have the same value, though, under the optimal value function, which could be the case. And then any policy that assigns any arbitrary probabilities only to those 2 actions is also an optimal policy. It doesn't matter how it's assigning probabilities to any one of these 2 actions that have the same value. But because the probability spectrum is infinite, it means that we have infinitely many optimal policies. So any one of these assignments of probabilities, as long as it's only on these actions that have the same maximum value, is also an optimal policy. And this is a simple example that shows that it can be infinitely many optimal policies then, but only ever one unique optimal value function. Okay.
So when we're talking about the algorithms and we find the optimum policy to get the maximum to get the evaluation return, so after that simulation, if I want to deploy these policies onto like an actual system, how much of a discrepancy would I see when I have it in like an actual like operating system? Because like when you explained the MDP, there are like many assumptions, but you know these are only assumptions, and in like a real scenario, you'll have like things that are different. So how would I then you know what would my expectation be on the performance?
Yeah, that's a good question. Okay, let's go back to this here. Okay, so first of all, let me take this in parts, your question. If the MDP that we're solving here is an accurate model of the real world, let's say that like this is a perfect description of the real world, then these evaluation returns are exactly what you can see if you take the policy at any one of these particular points in time. So let's say at this point in time, if I stop training and I take the policy from here and run it in the MDP, this is exactly the average returns that I can expect to see. And if I take it from here, then this is exactly what I expect to see, because these evaluation returns, they take the greedy policy, which is not what we do during training. During training, you will remember that we do the randomization so that we keep exploring different areas. But after training, we remove this line here. There's no randomization anymore. We only do the greedy stuff. And that's exactly how you would execute it in the environment. That's the first part of your question. But I think what you may be getting to is, what if the MDP is wrong, right? What if the MDP is not quite doing what the real world is doing? And that's a very good question. And that is exactly the reason why we care about reinforcement learning and not about dynamic programming. Dynamic programming needs the model. And even if we had the model and we could write it down, we could do all the sums and do all the expensive computation, there could always be this problem that you're describing, that the model might not reflect the real environment. But with reinforcement learning, I could apply reinforcement learning directly in the real world, where there's no model, there's just the real world. And so there's not this discrepancy, basically, right? So you can learn directly the data from the real world. In that case, there could still be problems with assumptions in reinforcement learning. For example, reinforcement learning still assumes that there is a Markov assumption, even if it's not actually using the real model. It still assumes that whatever the real model is, the real world is Markov. That already could be a problem, right? And then if that's the case, then there could be instability in the learning and other things. But that's one of the beautiful things about reinforcement learning, the fact that I can throw it at any problem. There can be any non-linearities. There could be a high dimension, and there could be lots of things that I'm not even aware of, right? Lots of noise, lots of things that are hard to specify, lots of coupled sort of differential equation effects. I don't care. I just throw it into this problem. As long as there's certain assumptions that are satisfied, like the Markov property, I have a guarantee that the algorithm still learns an optimal thing. And that's one of the nice things, right, about reinforcement learning. Really, really good. For example, I showed earlier, if I can stretch out the answer a little bit more, remember I showed you the warehousing example that we're building. Warehousing is actually a pretty complicated problem. There's very complicated time-dependent dynamics in the order profiles. As the orders keep coming in, it changes over time. And then your machines have vehicle models, which have nonlinear dynamics as well. Writing down everything in a warehouse like this would be impossible. I could not write down the stuff. I could not compute any of the stuff. And even if I could, it would be a mismatch with the reality. But we didn't have to. We didn't have to write down any of the stuff. We just train in the real world, basically. Or we have an extremely high fidelity simulator, which is trained with data from the real world. So that's why we're using RL in cases where classical approaches that assume all this knowledge or are not able to learn directly from the real world would fail. Yeah.
Perfect. Thank you so much.
Thank you. Question up here. Online questions? Sure, yeah.
Okay. I'm not sure, but I think that in some of the slides I saw that for applying like dynamic programming and this, can I say like pre-reinforcement learning algorithms, or that they are not
dynamic programming? Yeah.
We have to assume that we have like the knowledge of all of the whole environment and stuff. So for MDPs, there's just an approach with reinforcement learning or maybe deep reinforcement learning. So they cannot be approached with dynamic programming and these other partially observed MDPs.
Okay. Yeah, I should say, so first to make sure everyone understands the question. So I showed MDPs, Markov decision processes. And remember, I explained there's one assumption, which is that we see the whole world, right? The question here now refers to partially observable MDPs, POMDPs, which are a more complicated model where we're saying that we only observe something about the world, but not everything. Okay, that's a little bit more realistic now. And now the question is, can we still do dynamic programming in this kind of model, right?
Yeah, or that can they just be approached by reinforcement learning and deep reinforcement learning?
Oh, yeah,
or
for
policy
sure.
gradients?
Yeah, for sure.
Yeah.
So first of all, dynamic programming algorithms also exist for POMDPs, very sophisticated ones. And everything we do in reinforcement learning is under partial observability now. So for sure, we tackle these cases.
And would you say that, like currently at the state of the art, we have been doing more research in POMDPs than MDPs?
I mean, if I look at papers that come out, I still see papers that assume full observability. If they care about other kinds of problems, lots of papers care about partial observability. Almost all the stuff coming out of our lab is partial observability because it's more realistic, more complicated.
I mean, I would like to specialize in robotics. Would you say that POMDPs is more in the robotics world?
It depends. So I would say if you have a highly controlled environment where you have your proprioception and you have very reliable sensing, then it's kind of very close to full observability. And then to be honest, you can just treat it like that. And we've done that as well, right? And that's probably what you should be doing just to keep things simple. But of course, there would be many robotics applications where you have intrinsic partial observability because, for example, let's say, self-driving is a business that I was involved in. When you have self-driving vehicles, one of the biggest problems that we've had to deal with was occlusion. Occlusion means that there's cars here, and because of these cars, I cannot see what's like in front of them. Or there's someone parked here, and because someone is parked here, I want to get out, but I don't see the traffic coming out here. It makes it very hard for a control system, right, to deal with that. And these kinds of occlusions are very important, but can be dealt with all kinds of inference and reinforcement learning techniques as well. Yeah. I think we want to take some online questions. Yeah.
Okay, this question comes from the beginning when you were commenting about single agent versus multi agent.
Okay.
They were talking about that you said that a dimension of 216 is too big action space. And they were asking what would be a big but tractable action space with current reinforcement learning algorithms.
Yeah, I'm trying to get back to the slide. Where was that? Yeah, this one, right? Yeah.
Yep.
So the question is, what's actually a tractable action space?
Yeah.
Oh, interesting question. I guess someone should go ahead and try and figure this out. The answer to this question, I guess, would also change every year because things get better, right? So, what's a tractable action space? It's not just about the action space. It depends on the dimensionality of your observation vector as well. Sometimes you have a problem where observations are very small. Sometimes you have a problem where you have an extremely high dimensional observation vector. For example, let's say I have a robot that gets to see camera feed. It's a very high dimensional observation, right? That changes very quickly. And depending on how you define your observations, that could already be a big factor in terms of whether or not a problem is feasible before you even talk about the action space. So the answer to this question is bigger than just the action space. But this example is already enough to show that whatever the problem is, whatever the observation space is, even if it's a very simple observation space, that action space is already very hard to deal with for existing approaches. Yeah, I hope that people online can hear me okay. Did the person hear the answer okay?
Yeah, I think she did.
I mean, this is an interesting question. I want to ask back. I don't see the question, but the person who asked the question, if that person has any estimates based on experience they want to share, I'd be interested to know what they think is the borderline between feasible and not feasible. Or maybe, maybe people can do a little online guessing game and share their experiences, what they've been able to do and what was too hard for them. It would be interesting if people have experience using DeepRL, they can share, on Slack. What were they able to do and when did they hit a wall in terms of scaling? Okay, let's take some more online questions.
Okay, that one is from slide 40, and they were asking about what is the type of smoothing in the plots of the training curves.
Slide 40?
Yeah.
Okay.
If it's a smoothing in time dimension or a variation over the different seats.
Say again, what's the question?
About what is the smoothing on the back of the plot.
What's the smoothing?
Yeah, the smoothing colors, I guess. This kind of brownish.
Oh, you mean the shaded areas?
Yeah.
The shading, yeah. So this can be different in different plots. Most of the time, this would be the standard deviation or the variance of your evaluation returns. So to explain this, let's say we are at training step 100 time steps here, and we're going up to hit the purple line here. If we took the policy from here after this 100 training time steps, and then what we should expect to see in terms of evaluation returns is the point here. But because the environment can have noise effects, there's stochastic effects. Sometimes actions lead to one effect, sometimes to another effect. These are the probabilities that we cannot control. That's why there's variation in the returns that we materialize. And that's represented by the shaded area. So if the shaded area is very high, like here in the earlier days of training, then it means that the policy can be very all over the place in terms of the returns that you materialize. And that's because initially the policy will be not optimal. It will assign probabilities to actions that are not leading to good outcomes. But as you get closer up here to the optimal, you see that there's still some residual stochastic effect here, but it's much smaller, the shaded area, compared to the earlier days here. And that's because here we've now converged to the optimal value function where the only remaining random effects here are due to the stochasticity in the environment that we cannot control anymore. So yeah, that's basically what it means. Is that clear for the person online?
I think so.
Okay.
Okay. Another question is, do all actions have to be simple actions, or can you have a more complex action space? For example, each action is another subroutine. And if they can you have combinations of both simple and complex actions?
Yeah, for sure. So one idea that I think is worth mentioning is called hierarchical reinforcement learning. Hierarchical reinforcement learning means that your actions are now decomposed in a hierarchy. For example, one action could be something like clean kitchen, okay? Clean kitchen looks like sounds like one action, but actually clean kitchen could be decomposed in a hierarchy of actions, which includes move to kitchen, pick up, cleaning thing, whatever it is you use, clean objects A, B, C, D. And maybe the sequence of those actions make up the clean kitchen abstract action. So you have this hierarchy. And in this case, it's a much more complex composed action. In fact, you can be even more complicated with the hierarchy. You can expand the hierarchy and you can say that, okay, clean kitchen starts with move to kitchen. Move kitchen itself is a hierarchical action that's decomposed into turn around, accelerate, turn around again, like that, for example, right? So you can imagine how actions can be much more complicated and complex. And there's many algorithms that have been designed to deal with these kinds of complex actions. Another example is that actions can be parameterized. So for example, let's say we're playing soccer, okay, or football. And one action could be kickball, okay? But typically there would be a parameter like kickball and then strength. How hard do you want to kick the ball? So kickball would be a discrete action, but there could be a continuous parameter which decides just how hard to kick the ball, okay? Could be, for example, a value between 0 and 1. And again, there are algorithms that are designed to handle these kinds of composed actions. But here we kept it very simple. There was none of this. Okay. I think let's move on into the break because we still have the second part of the lecture and relax a little bit. If there's more questions, you can come to me. Happy to chat. And otherwise, I'll see you when shall we continue? 15 minutes? 12:15? Okay, see you at 12:15. Okay, good to go. All right. Yeah, welcome back, everyone, after the break. I hope you found the first part interesting. We talked about basic multi-agent systems ideas, learning in multi-agent systems. Why do we care about this? And then we went through some very basic ideas in single-agent deep reinforcement, in single-agent tabular reinforcement learning without any deep stuff. And this was our first sort of foray into reinforcement learning. And now I'm going to move into the multi-agent part by talking about the first piece of this bigger puzzle, which is games. We're going to be talking about just how to represent the world, nothing else. We're not going to be talking about how to learn in there. We're not going to be talking about how to evaluate in there. We will just talk about these different models to represent the world. Okay, so the first piece I think that we need to be really clear on. Okay. So as I said earlier, the slides you can find all online if you go on the book website. So there's no need to make copies of the slides here. There will be two parts in this lecture. First, in fact, three parts, the game models. This is the most important part here. And then we talk about some other things, such as how to model communication and also assumptions in some of these game models. Remember in MDPs, there were certain assumptions. Similarly, there's certain assumptions here as well you need to be aware of. Okay, let's get into it. As before, raise your hand if you have any questions, if anything is unclear. And if there's an important question online, feel free to interrupt me as well, okay? So there's a hierarchy of game models, and this is a one-slide graphical depiction of these different game models and how they relate with one another. Let's go through this, and we're going to go through some of these models in more detail in the slides. But you see, there's a nice diagram here. The first thing that you recognize already is the Markov decision process. This is the thing that you just learned about. There's only one agent, and there's multiple states that we sort of go through, right? So the environment has states and has a state, and that changes. That's the MDP. The easiest kind of game model now when we have multiple agents is the repeated normal form game, or the normal form game and then the repeated version of that. In this case, we have just one state, but we have multiple agents. Okay, you can see there's sort of the numbers are inverted here. MDP is one agent in M states, and now we have N agents and one state. Okay, there's only one state, or basically there's no state. Nothing in the environment changes, but there's multiple agents and they repeat playing a game. For example, rock, paper, scissors would be an example of that. And then there's the bigger class of games, which is the stochastic game. The stochastic game generalizes both the Markov decision process and the repeated normal form game. Now we have n agents and we have m states. So multiple agents and multiple states, but they're still fully observed. And then yet even bigger class of problems, and here gets really complicated, is the partially observable stochastic game. Now we also have n agents and m states, but also they're only partially observed. So there are n agents. They all may have their own reward function, their own preferences, and they also only see their own thing in the environment, which is not what the other guys might be seeing. It's quite complicated, right, if you think about it. And they're all learning in these games. So in this lecture, we're only going to be talking about these models, not about learning, not about algorithms and so on. We're not even going to be talking about what it means to solve these things. That's for tomorrow, okay? For the rest of the lecture today, we're only going to be talking about these formal frameworks. It's very, very easy. Okay, so let's start with the absolute simplest type of multi-agent model that exists, basically, that you can do. It's called a normal form game. Don't ask me about where this name comes from. It's inherited from the game theory literature, where a lot of this work comes from. I really don't know why it's called normal form, but that's what it's called, okay? Let's just go with it, basically. In fact, a lot of people call them matrix games because if it's just two players, you can represent it as a matrix, basically. But the general term is normal form game. It defines a single interaction between two or more agents. Let's just say two for simplicity. And it basically provides a simple kernel for all the other more complex models that you see later. So this is a good starting point. How is it defined? Okay, we're gonna go through this step by step. First, as defined with these as a three tuple, there's the set of agents, uppercase I. Call uppercase I because I is for index, and we use these indices in the actions and so on for the agents, and then the rewards. Okay, so there's a fixed number of agents, and coming back to the question that we had earlier here, this number of agents doesn't change over time, it's just fixed. Then for every agent in that set of agents, we typically use I or J to refer to the agents. Most of the time we use I. There's a finite set of actions that agent can pick from. For example, in rock, paper, scissors, there's rock, paper, scissors, 3. And every agent has its own reward function. Okay, and a reward function in this case is defined as a mapping from the combination of actions from all the individual agents into a scalar. So the big difference now between what we had before and now is that the reward function is not just a mapping from the agent's own action. The agent's reward can now be affected by the actions of all the agents. Okay, and this is called a join action. So the Cartesian product here of the different action spaces is called the join action space. That's probably the most important thing about the definition of a normal form game. The fact that all the agents have their own reward function, and the fact that the reward function is now affected by the actions of all the agents. Okay, that's probably the single most important thing. Was there a question here? No, it was just something happened there. Okay, so in a normal form game, there are no time steps or states. Okay, earlier I said there's just one state, but the fact that there's just one state that never changes, this means the same as that there is no state, basically. And agents choose an action and observe a reward. And it procedurally works like this. So first step, every agent samples an action from its policy. Okay, so as I said earlier, we're going to be using this index I to refer to this agent I. Every agent I chooses an action from its action space by using probabilities defined by its policy pi I. And then the resulting actions from the all the agents taken together is called a join action. So it's just a tuple here. And that is then executed, which leads to an individual reward for each of the agents defined by their reward function. So agent I gets a reward Ri, which is defined as an application of its reward function on that join action that was just selected by the collective agents. That's all. That's basically how one run of a normal form game works. There's different classes of games, and this applies to all the games we will be seeing. The most basic class that was studied in the early days is, and still is heavily studied, is called the zero-sum game. It's called a zero-sum game because here we say that the sum of the agents' rewards is always 0, hence zero-sum game. So formally it's defined like this. If we sum over the rewards that all the agents receive for a given join action, the sum will be 0. You could also say, this could be generalized to what's called a constant sum game, but constant sum games can always be mapped into a zero sum game because it's just a constant number that shifts. Okay, zero sum games. What's an example? An example is rock, paper, scissors. If I win, you lose. If you win, I lose. And if there's a draw, then we have the same, which is also zero. Okay. Another example is chess. Okay. These kinds of win-lose games are typically zero-sum games. The next class is a common reward game. In a common reward game, all the agents have the same reward function. They always get the same reward. You saw earlier this example that I showed you in level-based foraging where they picked an action and then everyone got a +1 reward. You remember that, right? That was a common reward game. And again, you can have this as a normal form game as well. And then the most general class is the general sum game. There's no restrictions on the relationship between the reward functions here. So basically anything that is not a zero-sum game or a common reward game is a general sum game. Okay, it's called general because there's no relationships between the rewards. None that are written down anyway. Okay, so here are some examples of what's called a matrix game. So we call them matrix games because if there's only two players, we can write down the reward functions as a matrix. Okay, looks like this. So for example, rock, paper, scissors is this game that I keep mentioning. We can write this down as a matrix where there's the three actions for the two players. So on the row player is one player which has RPS, and then the column player is another player which is also RPS, rock, paper, scissors. Let's say they pick a particular combination of actions. For example, the column player let's say the row player, player 1, picks action R for rock. And let's say the column player, player 2, picks action P for paper. Then because paper beats rock, player 1 gets a reward of -1 and player 2 gets a reward of +1. Okay, and it works the same way for these other entries here. If both of them pick the same action, rock, rock, then there's a draw. So they both get 0. It's straightforward, right? That's why we call it a matrix game. There's a few more examples here. For example, the coordination game. This is a common reward game, and that's why there's only one number in each cell because both get the same number. It's called coordination because they need to pick the same action. If they pick AA, then they get 10. If they pick BB, then they get 10. But if they miscoordinate on the actions, basically, which means that they take a different action, BA or AB, then they get 0. Okay, that's a common reward game. And lastly, example, Prisoner's Dilemma. This is probably the most famous, the most widely studied game in game theory. It models a situation where there's two people that are in prison. They cannot talk to each other, but they get interrogated by the police, and they have two options, each of them. They can either cooperate or they can defect. Cooperating means that they sort of stick together, they don't tell on each other, and defecting means they're going to say, it wasn't me, it was this other guy. Okay? And basically what happens is, if they both cooperate, then they both get 1 year in prison. But if, let's say, player 1 defects, I'm saying this is the other guy, and the other guy cooperates, which means he's not telling on me, then I'm going free and this other guy gets 5 years in prison. So you can see it's not a zero-sum game. It's also not a common reward game. It's what's called a social dilemma. How do they, what should they be doing in this kind of situation? It's interesting, right? So what is the right way to play this game? And there's many different answers to that. In fact, it turns out that most of the time the algorithms would learn defect, defect. And defect, defect is actually the unique Nash equilibrium in this game, which is theoretically nice, but practically not nice. It means that everyone is very selfish and always tells on the other guy. It's hard for algorithms to get away from that outcome because of various properties. Okay, zero sum, common reward, a general sum. Right, so that was the normal form game. And of course, you can do the same thing, but you can just repeat it. And now we're getting into the learning, because in order to learn, you need to repeat this experience to collect experiences. So a repeated normal form game is the same thing. We have a normal form game, which is defined, for example, as a matrix. And we just repeat the same thing over and over again for 100 times, for infinitely many times. Basically, if you show this as a graph like this, then there's only one state, there's only one node. The state is defined by this reward function here. And, if the agents pick actions 2, 1 to row 2, column 1, then they get reward 2-2. Oops, sorry. Where am I? Yeah. Then they get reward 2-2. So player one agent one gets reward 2, and the same for agent 2. But if they pick, for example, what is it, action 1-2, then agent 1 gets 0 and agent 2 gets 1, right? So and it goes on and on like this. So that's why probability of getting back into this state here is 1. And that's what a repeated game is. It repeats the same normal form game over and over time, over and over for a fixed number of time steps or for indefinitely. And now the important thing is the difference is that the policies can now actually be conditioned not just on nothing, which is what was the case in normal form games, but actually they can be conditioned on the history of the join action that they were executed in the past. So the history is this HT, and it means it's all the join action that were executed from time step 0 until the most recent time step. This is what they have seen so far that happened in the game, right? And sophisticated strategies can be conditioned on that. For example, there's a famous strategy called tit for tat, which is for prisoners prisoner's dilemma. And basically, it's just a strategy that is conditioned on the most recent join action, and it basically copies your last action. So if you defected most recently, I'm going to defect. If you cooperated most recently, I'm going to cooperate again. And tit for tat is an extremely simple strategy that turns out to be a really effective strategy for a prisoner's dilemma. Anyway, the interesting thing is now that we repeat this thing and also that policies can be conditioned on the entire history, but they don't have to be. For example, tit for tat only is conditioned only in the most recent join action. Okay, so that's it. That's normal form games, and that's repeated normal form games. The simplest thing that we're starting with for game models. Next, let's move into a more complex setting, which is the stochastic game. Stochastic game they're called that way because Shapley, who wrote this paper, stochastic games, in what was it, 1953, and he got his Nobel Prize in economics for a huge amount of work he did, including in game theory. And he called it stochastic games. They're called stochastic because there are now stochastic outcomes for the different actions you can pick, similarly to an MDP. Okay, so the generalization is now that we have both in there. We have MDPs as a special case where there's only one agent but M states, and we have repeated normal form games as a special case where there's N agents but only one state. But we have many more games where there's N agents but also multiple states. Okay, so how's it defined? Stochastic game introduces this notion of states, which can change over time, and it's defined by these 6 elements, which look like this. First, again, there's a finite set of agents, which is the set I. Then there's a finite set of states. Looks very similar to what we saw in the MDPs. And as we saw with the MDPs as well, there's a subset of states, which are the terminal states. This is when the game finishes. When we reach one of these states, then we've finished. For example, in the level-based foraging example, terminal state would be something where all the apples are gone. Okay, then it's terminal state. And now, in addition to that, we also define, similarly to normal form games, individual action spaces for the different agents. And also the agents have their own reward function as before, but now the reward function is a little bit more complicated. The reward function for agent I is defined as a mapping from the previous state and action that we took and the new state that we arrive in over a scalar. So this looks very much like the reward function definition for MDPs, except with the difference that the A in here is now the join action space, which includes the actions of all the agents and not just the one agent, okay? So similarly to normal form games, every agent's rewards, in this case, the reward for agent I, is defined, is affected by the actions of all the agents, okay? And lastly, like in MDPs, there's a state transition function, which defines the probabilities that we're getting into particular successor states when we execute a join action in a state. Again, this is defined over the join actions. So every agent's actions can, in fact, impact the probabilities. And lastly, there's an initial state distribution as we had before as well, like in MDPs. So it looks very similar to both MDPs. You can recognize certain elements like the transition function and the initial state distribution and so on. And it looks similar to the normal form games because you can recognize that there's these individual reward functions which are defined over the join actions. Okay. And also there's this number of the agent sets. So you can see how they're all special cases. We can write this down. Here's an example as a graph. Okay, so we can say that every state can actually be viewed as a non-repeated normal form game. Non-repeated normal form game just means that there is only one time we do the normal form game. And basically, let's say in this example, there's 3 states, S1, 2, and 3. And every state is defined by a matrix game for the 2 agents, which is shown inside the states here. Okay, you can see that every state can have a different matrix game to define the rewards in that state. And there will be an initial state. Let's say S1 is the initial state. And let's say, if we go through this example, let's say initially the agents, if they pick join action 2, both agents pick action 2, then the reward for them is 1-1. This is the cell in the lower right here. And then there's a probability with which we get into successor states. If we pick the join action 2-2, then with probability 0.5, we're going to go back into the same state. Or with the other probability 0.5, we're going to move into state S2. Right, so if we're in S2, we have a different reward function. And again, let's say if we pick join action 1-2, 1-2, then they get reward 0-4, and they're going to move into successor states. For probability 0.8, they're going to go back into the S1 state, or with probability 0.2, they're going to move into the S3 state, and so on. So you can see, like, it's a small, nice example to understand how to write down a stochastic game. And of course, I'm only showing a subset here of these arrows. I'm only showing you these arrows for some of the join actions. But in every state, you can execute any one of these 4 possible join actions, right? Combination of actions for both players, both agents. By the way, you sometimes hear me switch between agent and player. It's just because in my head, there's a lot of game theory literature, and in game theory, they call it player, not agent. So sometimes I accidentally say player, but for us, it means the same thing. Agent and player means the same thing, okay? In fact, in the book, to help people from both these communities talk with each other, I added a section at the end of chapter 3, which is like a dictionary for game theory and reinforcement learning, because we use a lot of terminology, but often this terminology means the same thing, like player and agent. So I added a dictionary that you can use to make your life a bit easier. All right, so let's look at this stochastic game as a process and go through this step by step. First, we have an initial state, which is sampled from the initial state distribution. And then at every time step, at this current time step t, every agent observes the current state. Like in the MDP, we're assuming that we get to observe the full thing. And then every agent chooses an action from its action space with a probability that's defined by its policy and also by which is conditioned on the history. I'm seeing, I think I missed the index here. I have to make a note about that. I think the index is missing on the policy, should be pi I. Slides 13. Okay. Will be fixed later today. All right, and then step, you can see that the policy is now conditioned on the state action history, which means all the past states and all the past join actions that were executed. So because every agent can see everything, they can also condition on the entire past. And then given the current state and the join action that was selected by the agents, we're going to move into a successor state for ST+1 with a probability that's defined by the state transition probabilities here. And lastly, every agent receives a reward, which is defined by its reward function. And the reward function is a mapping from the state and join action to the successor state. And as I said earlier, I think there was a question here. Really, most of the time, this is either defined only based on the actual state that we ended up in or just on the action that we executed in a particular state. But this is the most general way to write it down. In the book, in chapter 2, there's actually a section at the end where I show formally, theoretically, that the substates are still equivalent to this more general version, if you're curious. Okay, and then these steps are repeated until we hit a terminal step, a terminal state. For example, all the apples have been collected, or we reach a maximum number of time steps. So let's look at the level-based foraging example. This is the thing that I introduced earlier to give you a basic example of a stochastic game. How do we write this down as a stochastic game? In this case, let's start with the states. First, we have our states which are in the set S, And they're basically just a vector of x, y coordinates or positions for the different agents and the different items. For example, every agent and item has an x, y coordinate. Then there is a binary flag for each item, which is, let's say it's 0 if it's been collected and 1 if it's not collected, it still exists. And then you might also want to add elements in that vector to represent the different levels if they're not constant. So that's the state. The state is just a vector, which has the coordinates and which has the levels and so on. What's the next thing we need to define? Then we need to define the actions. In this case, it's just the 4 directions, up, down, left, and right. There's a collect action, which you can try, and then there's a no operation, which means nothing is done for that agent. And then the next thing we need to define is the state transition probabilities. In this case, it's deterministic. For example, if this agent here picks the action for going up, then for sure in the next state, it will be ending up here. So there's no probabilistic or stochastic effects here. And then lastly, the thing we need to define is the reward function. In this case, let's just say there could be a common reward, which means that everyone gets a reward of +1 if anyone picks any item, or it could be a different setting where we have general sum, where only a +1 reward is given to an agent that was actually picking up an item and the other guys get a 0 reward. So you can see how you can model this in different ways, but I think this is a sort of a neat, simple example that shows you how you can actually write down an example like LBF as a stochastic game. Does this make sense to everyone? Do you feel it makes sense? Any questions about this part? I think it's clear, right? Okay. Going back to this, the next thing, I think you cannot actually see the color here. This was, I think, supposed to be blue up here, but I'm gonna have to go back to this and change the colors maybe. Oh, you can see it on the sides. Okay, it's just a projector. Okay, great, thanks. Yeah, so now we're gonna move up to the last bit, which is the partially observable stochastic game, the most complicated, biggest, most complex model that we're looking at in the book. In fact, there's even more complex models that we don't even look at here. But here we're only gonna be looking at this because that's all we need really for most applications. Right, so partially observable stochastic games, as the name suggests, it's an extension of a stochastic game where we now have partial observability. In stochastic games, the agents could see everything, but now in a partially observable stochastic game, the agents have their own local observations. And basically that's what it means. Partially observable stochastic games are important for applications like self-driving, for example, where every vehicle only gets to observe its own local environment and estimates and so on, but not what the other guys are seeing. And in particular, if there's occlusion, then I don't see things that are behind these other vehicles, for example. That's very limited observability. Or if you can think about strategy games like poker, card games, where there's hidden information. I have my own cards in my hand that you don't get to see. You only get to see what's public on the table, basically. So there's public information, there's private information, right? So this partial observability is very, very important to represent in these cases. Right, so let's look at this graph again as an example. So a partially observable stochastic game is defined almost in the same way as a stochastic game. You see all the same elements here, except there's now 2 new things, which are the things highlighted in orange. Every agent now also has an observation set. These are the things that can be observed, so the observation vectors. And then there's an observation function, which defines the probabilities with which you get to observe these different elements in a particular state and so on. So yeah, so that's defined here. So for every agent I, we define additionally this observation set and an observation function, which gives probabilities over observing these different observations. So for example, in a self-driving case, you might have noisy observations. Okay, so if I have estimates about the locations of the other vehicles, these estimates might be noisy in the sense that they might not be completely accurate. They might be slightly off the mark. So there's a noisy element which is represented by this probability distribution. It could be, for example, Gaussian covariances, and then your estimate isn't exactly right center. Or you could have observations where the full state is defined with everyone's locations and all the apples and all the agents, like in level-based foraging, but the observation vector only includes the location for one agent, ourselves, for example, and maybe only the location for apples which are in the vicinity of, let's say, a square of 3 by 3 or something like that. Okay, I'm just making up examples basically of what partial observability could be. And you can represent that all here. Here, this is the same graph that we saw earlier. I'm just showing this dashed line here because to represent that the agents do not directly see the state anymore. Instead, they receive an observation that depends on the state, but doesn't tell them exactly what the state is. And that's kind of difficult to write down here as a graph. So we just use the dash basically to explain what that's supposed to represent. Again, process, very similar to before. We start with an initial state, and then every agent receives an observation. There will be an initial observation, and then subsequently there will be observations sampled using the observation probabilities here, which depend on the state that we are in and also the previous join action. We may or may not observe the actions of the other agents. They may all be completely unobserved. And then every agent chooses an action AI at the particular time t, which is based on its policy pi I, but now the policy is conditioned on the full history of observations that the agent has made from time step 0 to the current time step. And then, the agents pick their actions, and that's the new joint state action. The joint action then affects the state of the environment just like it did before, and just like it was before, every agent gets a reward as well. And this is done until we reach a terminal state or we have reached a maximum number of time steps. So the only thing that's new here is these two steps where the observations are sampled and then the agents get the condition on the sequence of observations that they observed in the past. But other than that, it's the same. Okay, here's again an example, but I think the colors are not ideal again. I think you can see this on the slide, but not here. This is supposed to be a shaded area which shows what they get to see and what they do not see. So if you look at the slides, you can see that this is a gray area here. And basically what this represents is, this agent here only gets to see this and this apple, but not the apples outside the visibility region. And similarly for this guy here, it only observed that apple, but not the other guys. So in this case, we model limited visibility. And this is also important because, what they see really changes what they need to be doing. We're going to talk about this in just a second here. Yeah, in fact, here. So there's an important thing now, something that didn't exist in the fully observable case, which is that the fact that we only make these limited observations, it means that we do not know what the actual true state is of the environment. And that means that it may not be optimal to make choices that are only conditioned on the current state that we're in. What we really need to be doing is we need to make an estimate on the real state of the environment based on the observations that we've received over time. So what do I mean by that? Let's say we're in this particular situation that we're seeing here. And let's look only at this agent here on the left. And it has this observability region, which you cannot see, but this is supposed to be gray. You can see this on the slides if you look on your computer. And the optimal action for this agent here is to go left because its level is level 1. The other apples that it's seeing are level 2. They don't make sense. And the closest level 1 apple is the one on the left here. But it doesn't know that the apple is there because it's not in the visibility region. So it doesn't know what the optimal action is. So if it only conditions on what it's seeing right now, it wouldn't know what to do. At the very least, it would know that it's not supposed to be collecting these apples here. But what it could do is if it did, in fact, previously move around here, and it previously was, for example, down here where it did see this level 1 apple on the left, then it should have some sort of memory functionality to remember that there is, in fact, this apple here. I saw this previously, right? So I need to remember that, okay, there's this thing here. Maybe I need to move on the left, even though I don't see this right now, because I previously saw there was something there. And the mathematical vehicle to do this is called a belief state. A belief state is a distribution over the possible states in the environment, which is called B for a belief state. And basically, this is computed by using something called Bayesian theory or Bayes law. Hands up if you know Bayesian theory, Bayesian probabilities. Okay, surprisingly few people. Really, only less than half of people know about. It's probably one of the most important things you need to know when machine learning. Bayesian probability. If you don't know about Bayesian statistics or Bayesian probability, then learn about it right now today. Basically, go home and learn about Bayesian probability. You need to know about this because a lot of the machinery mathematical background in machine learning is based on Bayesian theory. And Thomas Bayes is actually an interesting background. Thomas Bayes, who's, it's named after him. He was actually a reverend, a priest, and he apparently invented Bayesian calculus to prove the existence of God. I don't know how well that worked out for him, but it turns out it worked out really well for machine learning. And also Thomas Bayes also he was also at Edinburgh University. He actually studied medicine. Anyway, that's described in the book, but basically it looks like this. Let's say for simplicity, there's just a single agent, just to keep the mathematics a bit easier. There's not multi-agent, just a single agent, but there's still the partial observability. Let's say initially we know the distribution of states initially. Let's just say magically we know that. So that's our initial belief state. And then we do this update process. After taking a particular action, we make a particular observation. And assuming that we know the observation probabilities and also the state transition probabilities, we can apply this update here. So our Bayesian posterior over the state space will be updated to be proportional to this calculation here, which is basically summing over all the states we could be in, summing over all the successor states that we times the probability of the successor state when observing the successor state, and also times the probability of observing that particular observation in that set. And that's this is just the proportional to sign, which means that you can turn this into an equation if you add a denominator here, which is just summing over this for all successor states. That's based on probability, very straightforward. But the reason why I'm showing this here is because this type of inference is typically infeasible, not just in multi-agent RL, already in POMDPs. You mentioned earlier POMDPs. This type of computation is a standard process in POMDPs, but no one does it because it's not feasible computationally. In practice, you would use other kinds of inference techniques. For example, deep learning can be trained to infer states implicitly through sequences of observations. That's why deep learning is also a useful thing for these kinds of applications. Okay, the other reason is why we do not do this in reinforcement learning, including in MARL, is because we don't actually know these ingredients. We don't know the state transition probabilities, we don't know the observation probabilities, and then hence we cannot actually compute this analytically. But I wanted to show you this because this is important. In any case where you have partial observability, you need to maintain some sort of memory functionality in order to recover information that you observed in the past that might be relevant for an optimal decisions. And in POMDPs, which is the version when there's only a single agent, the optimal policy is actually defined over the belief states, not over individual observations. And it's called a sufficient statistic. It summarizes all the information that you observed in the past. But practically in reinforcement learning, we cannot do this because we do not know these pieces of information. Even if we did know these things, to be honest, we would not be able to do these marginals. There might be billions of states. It's impossible to sum over these states. Okay, so those were the models. Okay, so we started with normal form games, just one interaction, but with multiple agents and just one state. Then we went into repeated normal form games. We repeat the same thing over and over again. Then the next general class is stochastic games. We now have M agents and N states. Okay, includes MDPs and normal form games. And then we looked at partially observable stochastic games, which is when we now also have the case that agents have individual observations. Those are, in my view, probably the most important models you need to know about if you want to learn about multi-agent reinforcement learning. And that's all we cover in the book. In the book, these things are described in a good amount of detail. For the rest of this lecture, before we wrap up, I just wanted to talk a little bit more about some communication and assumptions, because I think a lot of people are interested in this. First, communication. So in many cases, in applications and so on, you can imagine that the agents can actually talk with each other, right? They can send messages. They can say, they can send symbols, ABC, and then these symbols can mean something, or they can actually send proper messages as text. If these agents are equipped with some sort of LLM functionality, they can send whole sentences to one another, right? And interpret those. So we can use these existing games as they are to model these communication actions. And basically the way you can look at this is that communication is just a type of action. We don't change anything about the model, it's just a type of action. It just happens to be that this communication action doesn't change anything in the environment. It can be observed, there can be noise and corruption, but it doesn't change the physical state of the environment. But because it can be observed, the action, it's like communication, right? So they're sending each other these signals. We can view communication as a type of action that other agents can observe without affecting the state of the environment. And then agents, the cool thing about multi-agent reinforcement learning is that the agents can actually learn to attach meaning to these communication messages. So one of the really cool things about multi-agent reinforcement learning is this idea that the agents learn together to come up with the language, to come up with a particular way of attaching meaning to different symbols that makes a lot of sense for them, but maybe doesn't make any sense for us. But it might make a lot of sense to them in terms of solving the task. So how do we do this? For example, we describe this in the book. You can say, now the action is just a slightly more complex, composed of two spaces. One is a physical action, X, and then one is a message, M. And it's basically just a concatenation of these two things. But it doesn't change anything about the models. Let's say in M, there could be multiple messages you can pick from, different words, different letters, different symbols, and so on. And every action is basically just a combination of a physical action and a communication action. So agents observe the current state as before in a stochastic game. And then, if they observe each other's actions, that means it includes the communication action, so they can observe the message that the other action sent, basically. In a partial observable stochastic game, it's similarly modeled. We can say that the observation now includes some kind of information about the state, but it can also include the messages, W in this case, from the other agents. And because of the observation probabilities, we can even model things like noisy messages, if it's a noisy communication channel, or loss of messages. We can model that these things could be empty as well and under certain probabilities. So you can be really quite creative with how you model this. That's all I wanted to say about communication. The last couple of slides, and then we finished for today, is about assumptions in games, because I think this is important to be aware of. So first of all, a lot of this work comes from game theory. And game theory is much older than reinforcement learning. And they have their conventions and their assumptions, and some of these assumptions make sense, and some of those assumptions maybe don't make so much sense. But it's important to be aware of those assumptions, because if we do not assume the same assumptions when we talk with each other, we're not talking about the same thing. First thing we need to get right when we talk about each other is, what are actually the settings and the assumptions? Very important. So in game theory, if we start there, we typically assume that all the agents know all the components of the game. It's called complete knowledge. This is the default assumption in game theory. So for example, in a stochastic game, they know all the action spaces, all the state spaces, the probabilities of the state transitions, and so on. They know the complete definition of the stochastic game, including the reward functions as well. So I even know what your preferences are, what your reward function is. So by extension, I know what your rewards you're getting. Okay. That's the typical assumption in game theory. But now let's look at MARL assumptions. In MARL, we typically have limited knowledge. And that was the same thing that I said earlier in single agent compared to dynamic programming, what we assume in temporal difference learning. Most commonly, we do not assume that we have knowledge of the transition function. And we also typically do not have knowledge of the other guy's reward functions. We may at best know our own reward function, but we may also not even know our own reward function. We may only experience our rewards as we try things in the environment. Okay, then you can have additional things. For example, certain agents may know certain things about the game that you do not know. So knowledge might be mutual. If there's certain things about the game that everyone knows everyone's reward functions, or it might be asymmetric. So you only know yours, but not mine. Maybe you know something about the state space that I don't know, and so on. So, in realistic applications, it could be that the agents have different domain knowledge. And also, this comes back to the question earlier. We typically assume that the agents are fixed, the number of agents, but there is research, including from our lab, where we have this open multi-agent system. So there can be a dynamic number of agents. They come and go. And lastly, I think this is the last slide. This is this dictionary that I showed you earlier. I think this is quite useful. When we first announced the book more than a year ago, one of the first things that some people did on Twitter was Twitter then. So they copied this the dictionary and shared it a lot with their friends, and it got shared a lot. And for us, it was surprising that this was one of the most important things that some people took away, because I think there was a frustration about this idea that the language was just not aligned. And here was finally like a table that actually just brings it together. But basically, it's quite straightforward. In reinforcement learning, we often use this term environment. In game theory, we call it game. Game is also the term that we used just now here. Agent and player is the same thing. in reinforcement learning, we call it reward. In game theory, it's typically called payoff or utility. Then there's the policy, which they often call strategy, and so on. Deterministic policy is what we would call it. They would call it pure strategy. So you see, there's different terms, but they really all mean the same thing. And we just need to be aware of those things, and then we can talk with each other again. Okay, that's all we need to do, basically. But in the book and in the lectures, we're going to be sticking with the reinforcement learning terminology because that's ultimately what we care about and what we do. Okay, I think that's it. So we covered the game models. We covered some basic things about communication and assumptions in games. And then tomorrow we're going to be moving into solution concepts for games. So what does it even mean to solve these games? We haven't even talked about this, right? I haven't told you yet what it means to solve any of these games. And there's in fact many different solution concepts. And the other thing we're going to be covering, I think tomorrow as well, is so some basic, very first basic ideas for how to do reinforcement learning in these kinds of games. That's what we'll be doing tomorrow. Last thing I want to say is do take your time to go through the book sections and the slides. If you have time, you could already look at the chapter for tomorrow if you want to make it a bit easier for yourself. And starting later today, I'll be posting the link to the coding exercises on the Slack channel. And that will bring you to a README file that explains very easy, step-by-step, some basic instructions for how to run some of these algorithms in things like level-based foraging. So again, this is optional. You can do this in your own time, and it shouldn't take more than 1 or 2 hours, really. But one thing I want to say is, in fact, I can actually show you already. I think I actually have, yeah, it's here. So basically, I will be posting this link here, and it gives you exercises for the Barcelona summer school. Basically, starting from tomorrow, day 1 is supposed to be tomorrow in terms of the coding exercises. It gives you all these steps you can basically go through, and how to use the code, how to run these algorithms, and so on. And there's some very basic exercises about how to evaluate some of these algorithms and get some early results. So it's really not a lot, but it's meant to give you something to start with, to play with, right? And then you can go from there and just play basically and do more things on your own. So yeah, with that, I think let's wrap up for today and see if there's any more questions. Yes.
So in these examples, we had essentially environment with discrete times. We have time steps. Will we be looking, or is it like generally a thing to have continuous times and asynchronous actions, or we always assume that it can be approximated by discrete steps and maybe some default actions?
Yeah, very good question. So the vast majority of the literature is like that, discrete time steps that you can implement in some sense. Personally, I'm only aware of very little research in reinforcement learning that looks at this idea of continuous, where there's not a discrete delta t, basically. Just last year, I gave this talk in Canada at University of Alberta, and Rich Sutton is one of the grandfathers of reinforcement learning, did this book, and they had one paper in this space, and that was the first paper I ever saw that does it like this. It tells me that there's probably very little does it like this. But then, to be honest, in practice, it's not really a big deal. In practice, in the applications we're building in robotics and so on, there's ways to handle this. One is you can have like a very high frequency in the action space. So in self-driving, you're looking at a very minimum 10 hertz, which means 10 decisions per second. So between every decision, you have 100 milliseconds. And that's quite low already. Like typically 20 or 30 hertz would be better. But what I want to say is if you execute, for example, 10 hertz, 10 times a second, it means that the information that you collect between these delta t's, you can still accumulate in a filter. It's called a filter, basically, that gives you a state estimate. So it's not like you're losing information in between. The system can still maintain this information. And if the frequency is high enough, 10, 20, or even 100 hertz, then you're so close to real time that it almost doesn't matter anymore. So for example, it's been found that professional human players who are extremely good at their job, like professional human players in StarCraft, they are, I think, working with a framework of typically a frame rate between 30 and 60 frames per second. So that's what humans do. And they normally speaking, operate in real time, not in discrete time steps, right? Basically, but the brain is wired in a way that there's not more capacity than that, basically. And if robots can operate even more 100 hertz, then that's already more than what humans do, basically. And then, look at other examples, high frequency trading in financial systems, they need much more than that, right? So 10 hertz would not be enough for them. Okay, but I hope that answers the question.
And also for actions in these high frequency cases, I guess like we don't need to actually have active actions from all possible agents. We can have some no-op, for instance, right, to fill the joint action.
Oh, yeah, that's interesting. So your question now is, if there is a delta T, but in reality, these agents might not be always making the decision exactly at this T time step, right? So it could be that for one agent, it's now, I want to make a decision, but the other guys are not there yet or whatever, right? Then, yeah, how do you deal with that? I think there's a few ways of dealing with that. You can say there could be a no-op, which is what you just said. Or there's protocols where you say we always wait for everyone to be ready to make a decision, and then there needs to be a central coordinator who says it's decision time, basically, and then it broadcasts decision time, and it waits for everyone to make a decision. That's another protocol to deal with this. Another way to deal with this is that if I do not have any components in my system that explicitly rely on having information about your actions, if everything in the system that I get to observe is purely based on my sensing network and not this is your action, then I don't care. I don't care when you make a decision. I just get to see whatever I see in my camera, for example, right? So it's different in that sense. It's only important if your particular algorithm has a discrete component that explicitly represents the other guy's actions, which probably is not a good idea anyway for deployment cases for those reasons. Yeah. But there's lots more ideas and it can be quite creative. So, we can talk more about that basically.
Thank you.
Okay, this is an online question.
Okay.
They were asking, when you are mentioning communication between agents, how we accomplish currently in real world multi-agent deep reinforcement learning, specifically multi-robot warehouse system, any communication protocol?
What's the question? How accomplished are we in terms of learning communication protocols?
Yeah, in real world.
Okay. So we don't actually do that. In our warehousing application, we don't learn communication protocols like that. There's a different system where there's a manager agent that is learning to dynamically allocate tasks to the worker agents, which are the humans and the robots. And the robots in turn learn to execute those actions. And so they're learning simultaneously. The manager learns how to assign the tasks, and the worker agents learn how to execute them. But there's no communication in the sense of talking. I think this research in learning communication protocols is still not very advanced, to be honest. And that's because it's not easy. Learning to attach meaning to symbols is an entire research area, even outside multi-agent reinforcement learning. So we've worked with people who are not reinforcement learning or machine learning people who study languages, and they have what's called a language and reference games, and they basically study how agents attach meaning over time to symbols. But it's not really about reinforcement learning or about solving tasks. It's purely about this idea of emerging a language together. And there already I can see like it's still a very difficult process to converge robustly to a shared language. There's a lot of complexity going on. There's a lot of issues with when you observe locally things. I think that if there's PhD students here and you are really interested in communication and learning communication in multi-agent reinforcement learning, it's probably a really big opportunity space for you, because I have not seen there are papers, and there are still papers coming out these days where they try to develop multi-agent RL for communication. But every time when I see these papers, I think they're not very scalable yet or not very advanced yet. So I think there's probably a lot of opportunity for you if you're interested in that space, including the people online who asked.
There's another question about if you know that if MARL is currently applicable in the stock market prediction space, or there are too many agents and it's a very dynamic environment to be this is a realistic application.
So I'm not really a finance guy, but I'm aware of some companies who are trying to do this, and spoken with them as well. I think probably my short answer is I don't know. I haven't really explored this application so much. but I can see some problems already, basically. One problem is with trading, I think there could be situations where you have really many agents, hundreds of agents. Whereas a lot of the algorithms currently in multi-agent reinforcement learning are not designed to scale to hundreds of agents. They scale to tens of agents typically. I think there's still a lot of work to be done in terms of scaling to hundreds of agents. And it's not clear yet what the right philosophy is there to achieve that. There's mean field games which make certain abstractions to achieve scalability, but they have other limitations as a consequence. Yeah, so although I'm not familiar with this application so much, I would already expect that there's certain limitations in multi-agent reinforcement learning when it comes to scaling to these applications, I would say. Yeah. Any more questions here? Yes, there.
Is it always a kind of decentralized agents, or can we also think about a central agent which takes in, which gets communication from other agents and then kind of commands the different agents?
Yeah. That's kind of so tomorrow we're going to be talking about this idea of a central learner, which is like this. And it's similar to what I said earlier when I gave you this example in level-based foraging and how we want to decompose the problem. Because if we have a centralized agent, you would have this exponential action space. 216 was the example, right? Which would be very hard to deal with. So centralized learners are typically not feasible for that reason. But there's ideas in between. For example, what we do in the warehousing application, we have something that's kind of like a centralized agent, which is this manager agent. The manager agent is responsible for allocating tasks to the individual worker agents. So it's like a central component that coordinates them. You do this, you do that, you do this, and I'm trying to coordinate you. But I'm not actually telling them exactly how to do this. They still have to learn how to do these things, which makes it feasible, basically. But if I had a manager agent that told everyone exactly, you do this and you do that and you do this, and this is exactly how you do everything, then again, we would have this problem. It would not be feasible. It would go to this large action space. So it's an example of an in-between where we have decentralized worker agents, but there is something like a high-level centralized entity that has more information, but makes decisions on a high level that makes it still feasible. So you can see multi-agent reinforcement learning really gives you a lot of flexibility in terms of shaping up these configurations of agents and their action spaces. And whatever configuration you come up with, you can still use whatever existing multi-agent reinforcement learning algorithm to optimize the policies for these different things, which I think is really cool.
Yeah. Another question related to this. So, for example, if we think that we have infinite compute and everything else, is there any study which shows that the completely decentralized option can achieve the same efficiency as that of the centralized?
Even without the limit case, my experience is that the decentralized cases kind of always are more efficient than the centralized case. And that's because they're facing a much smaller decision space. But they have other problems. And they could, for example, have chaotic behavior, which means they don't converge to an interesting fixed point, which will not be the case with the centralized one. If it's a well-defined central single agent reinforcement learning algorithm like Q-learning, and if those assumptions are upheld, then we know that it's guaranteed to converge to the optimal Q function over the joint action space. But because it's a very large search space, 216 actions in this example, at every time step, 216 is in a huge, gigantic branching factor. It would be very inefficient, would be very slow to achieve that. Whereas if you have these multiple decentralized learners, they typically learn much faster to fill the values in these much smaller value functions. But they may not coordinate well. And in that case, there's a different kind of problem in this sense. If you're asking about efficiency, I would expect that practically they would be more efficient, but they might have other problems, which is that they might not converge to the actual optimal solution, basically. Yeah. Does that make sense? Yeah. Okay.
Thank you.
More questions here.
Yeah, I was going to ask something similar regarding the decentralized and centralized approaches. I've read a lot in the literature that this concept of centralized training and decentralized operation. I don't know if this is the the most popular approach or something like that. And then you mentioned that you can train in a decentralized manner. And if so, well, it's kind of a question within the question. I don't know if you mentioned this in the earlier part of the lecture because I came a little bit late, but what would be the difference with swarm intelligence? And if swarm intelligence is like a kind of research that is getting behind because of the multi-agent reinforcement learning, or is in parallel?
Yeah, okay. A lot of questions. So I think swarm intelligence, I'm not so familiar with their latest techniques, but I know some high-level outlines. So with swarms in this type of literature, we look typically at hundreds or thousands of agents. And due to the need to scale hard to these many agents, we typically would not have the capacity to run individual reinforcement learning processes on hundreds or thousands of agents simultaneously like that. Instead, they use highly simplified, typically heuristics-based approaches that are hard-coded into FPGAs that can be executed locally on these systems. So it's typically not learning-based, and if it is learning-based, they would not be scaling to so many agents. That's the papers that I've seen, and in that sense, they don't really tend to use multi-agent reinforcement learning. They tend to use much simpler approaches to achieve the scaling. That's typically the trade-off, right? Here, we still have quite a bit of compute that needs to be done to do this type of training. So even though I'm not in this community, I do see papers sometimes. And as far as I'm aware of this community, I think they tend to use highly simplified approaches just to achieve the scalability. And then with the simplified approaches, they want to see if they can still have interesting emergent behavior if everyone works like this. For example, one sub area of literature is called flocking, which means if you have hundreds of agents like drones, and you can insert some agents that you can control, how can you manipulate the whole flock and flocking to do certain maneuvers, basically? And tend to use really simple approaches. So that was the last question, I think. Repeat. The first question was about centralized training and decentralized execution. Yeah, so I'll be talking about this not tomorrow, but after tomorrow. And yes, it's a very important paradigm. And it tries to combine the benefits of both these ideas. Centralized training means that we have an opportunity to train everything in one place. For example, we can simulate the environment, we can control all the information, they can communicate completely, there's no limitations due to the real world. We can train them centrally, which gives them maybe a better environment to learn useful things together because they can share a lot of information. But we're training models that after training can be executed completely independently. So centralized training with decentralized execution, that's where the name comes from. And that's useful because it's often the case that we do have the ability to share a lot of information during training. That could be like everything is trained in one place. We are not constrained by hard physical, for example, limitations if everyone is in the same lab. But then if we can train it so that post the training, we can then execute them still locally, that might then satisfy the requirement of the actual application. One direct example I can give you is something like self-driving. You can imagine that you can train self-driving policies in a large simulator like Carla is one of the most popular simulators, and you can train policies for tens of vehicles. And because they're all trained in simulation, they can share a lot of information, right? That could be useful. But of course, in reality, they cannot share all this information. Still, we can train those policies so they can be executed after training in a fully localized way. And that's kind of the interesting, like the beauty of this centralized training with decentralized execution aspect, that you're trying to do it in this way that can be executed locally. But what in theory, what would be even nicer than this is decentralized training and decentralized execution, right? Because then you can do everything on the actual deployed system. You do not have to have this ability to share privileged information during training. And it turns out before the deep learning phase of multi-agent reinforcement learning, the work that came out in the early 90s, that was all decentralized training and decentralized execution. They did not have this concept of centralized training and decentralized execution. This only came later when the deep learning stuff came in. So the early algorithms, which we discuss in chapter 6 in the book, which have a lot of the theoretical claims, they were designed for the decentralized training, but they do not scale to the interesting applications that we care about. And that goes back to the question that we had earlier here, when you asked about the centralized and decentralized efficiency. There are a lot of early algorithms in multi-agent reinforcement learning that have hard guarantees in the limit to learn particular solutions like a Nash equilibrium. But they typically do not make claims theoretical claims about finite time efficiency. It's only ever in the limit. And in fact, the same goes for single agent reinforcement learning. Almost all the literature is only makes claims about the limit performance, but not about finite time bounds, basically. So it's hard. This question that you asked when I gave you this answer was just my empirical answer. But theoretically, there's very little in terms of finite time bounds that would actually compare the efficiency of these learning processes. Another question there?
So but if it is decentralized training, would it achieve the same level of interactions as that of like centralized training? Or because that's one of the goals, right? Of multi-agent reinforcement learning, to have the interactions between the agents.
Yes. What do you mean the same level of interaction? What do you mean by that?
Basically, what I mean is if they're like decentralized and decoupled, how do they interact with each other? Like, how do they take into account the action space of the other agents?
They could still do that, right? Even if a decentralized case, they can still represent these other agents and that they choose actions. They don't have to, but they could. I think maybe this isn't the right question. The real question is, I think that's what you want to ask, is can they still learn the same solution concepts as centralized approaches? Because that's what matters at the end. We want to learn a Nash equilibrium, for example, which I'll tell you about tomorrow. It doesn't matter how interactive that is or whatever that even means, that concept. The only thing we care about is that we learn a well-defined solution that satisfies certain properties. For example, in a Nash equilibrium, it means that everyone's policy is mutually optimal with respect to the other policies. So that's a hard, like a concrete mathematical set of properties that we want to satisfy. And the real question is, do the decentralized learners give us a guarantee to learn these concepts? And yes, there are many algorithms that have these kinds of guarantees, except for the more recent deep learning-based approaches where most algorithms do not have hard guarantees because of the empirical nature of this work and because of the nonlinearities in the function approximation, which is hard to do any theory then there. Does that make sense what I'm trying to say? I'm trying to shape your question to be more about the endpoint of the learning. I think your question was more about sort of during the learning, how much they interact, but actually what really matters is what solution they learn. The solution defines really what we care about.
But the solution also is a result of the training process,
yes,
right?
Yes. But during training, anything can happen, right? I don't really care what they do during training. What I care about is that they give me this thing at the end, which is, for example, a Nash equilibrium. And different algorithms may do it in different ways. But as long as they give me the correct answer, which is a Nash equilibrium, as an example, then that's what I wanted. And whether it's centralized or decentralized training, at that point doesn't matter anymore. I just have my Nash equilibrium then, basically. That's like the result of the learning that I wanted to get. And I think this will be more clear tomorrow when we talk about the solution concepts, which we haven't talked about today.
Thanks.
All right. And more questions, or are we good to wrap up? I think we're probably good to wrap up. So anything online we want to do quickly? Okay. And then we can wrap up.
One is asking if can you please further elaborate on limitations on mean field game MARL?
Oh, okay, interesting. Yeah, I guess there's someone online who knows about this. So mean field games, as the name suggests, I'm going to keep it short because I think it's not relevant for a lot of people here. It takes population averages. It reasons, the policies reason over what a population average is doing, which means I don't care anymore about differences in policies between individual members of the population. So I can achieve a lot of scaling, but the drawback is that I have a homogeneous population where everyone uses the same policy, basically. And in many applications, that's not what I want. I want people to have different policies because teamwork necessitates that they have different roles in the team, they complement each other's actions and so on, rather than reasoning over population averages and aggregates. That's my short answer.
And the other one is in a nutshell, what are the different multi-agent system types, excluding Swarm and MARL, we have already discussed?
The different multi-agent systems types. Yeah, I'm not sure I understand the question. I guess, yeah, I'm not sure I understand the question. There's multi-agent systems where there's always an environment and multiple agents, and they have different observability, reward functions, and actions, and so on. I'm not sure what's meant by types. Different types of algorithms. Okay. Oh, I see. Yeah. I guess there's different categories of algorithms. For example, tomorrow we're going to be learning about independent learning and central learning. After that, we're going to be learning about things like centralized training with decentralized execution. These are broader categories, and lots of algorithms exist in these spaces. Yeah, so and then you can also, further refine these categorizations. Different algorithms have different assumptions in terms of what they get to see and what they do not need to see, in terms of what they need to know about the game, what they do not need to know, and so on. Assumptions in terms of the rewards. Do we have common rewards or zero sum and so on? So I guess the categorizations that I showed you earlier, such as the different classes of games, they also sort of apply to the algorithms in some sense, because different algorithms are sometimes designed for different classes of games, like zero sum games and common reward games and so on. I guess I'm not sure if that was the question, but let's say that's my answer for now. Okay. All right. Then I guess we're good to wrap up, right? One more question there. Okay.
Makes learning more efficient when we have a huge action space.
I would say can
make. Yeah, whenever it's not chaotic and it's an optimal solution is possible to find. And I'm guessing maybe it also has to do with the return design, or the way we can decouple that also.
Sure.
Because like maybe in one single reinforcement learning, we have like a Pareto front we want to optimize, and you have to design a very complex reward function. I don't know if multi-agent reinforcement learning can ease that by having multiple agents.
Yes. So I think the things that you just mentioned, we're going to be talking about this tomorrow when we talk about solution concepts. Okay. So maybe the answer is too big for this, right? I think everyone's already a little bit tired. Maybe let's bring the question back up tomorrow, because tomorrow we have the background to talk about this kind of question. Okay. So we'll come back to your question tomorrow. Okay. Sound good? All right, then. Yeah. Thank you, everyone, and I'll see you tomorrow then. Okay.